Добрый день.
Dear all, I'm very glad to see all of you here, and it's a great honor for me to open the Anosova anniversary conference, and it's time for a formal part. I'm happy to introduce Dmitry Treshchev, the director of Steklov Institute of Russian Academy of Science, who is going to say a few words at the beginning of our conference.
Thank you, Sasha. Dear colleagues, dear friends, I am happy to see many names, many participants. Unfortunately, we don't have a possibility to meet as frequently as before. That pandemic. And just a few words about Dmitry Viktorovich Anosov. In fact, he is known to the mathematical community as the first mathematician to understand the role of hyperbolicity in dynamics. He was inspired by his scientific advisor, Lev Pankryagin, and especially by Stephen Smale, but that was his personal discovery. And Anosov was a profound and maybe in a certain sense pedantic mathematician. And in fact, the theory of hyperbolicity contains several very delicate effects, which are connected, first of all, with some smoothness aspects, smoothness of the corresponding foliations. And you know that at this point, some his, in fact, brilliant colleagues were somewhat careless. Scientific career of Anosov was connected with Steklov Mathematical Institute and Mechanical and Mathematical Department in Moscow State University. And he was a head of two very important seminars joined with Stepin on McMat and joined with Ilyashenko here in Steklov Institute. I had just a few personal contacts with Dmitry Viktorovich, but he supported me in several important situations, and so this conference is a joint event by Steklov Mathematical Institute and the Higher School of Economics, and this is another reason for all us to remember Dmitry Viktorovich Anosov and to share recent achievements dynamics. So enjoy good company, enjoy good mathematics. So we can start probably, yes.
Okay, I probably just thank you very much, and I'm going to delegate the duties of the chairman today to Yuliy Sergeyevich Ilyashenko. So, Yuliy Sergeyevich, go ahead. You're the boss now.
Okay, Alexandra Sergeyevna, thank you. I'm not absolutely sure that we should start before the announced time. So Alexey and Dmitry Valerich, what do you think about that?
I guess we should start as planned at 1 p.m. exactly.
Yes, I agree.
Well, so we have a 15 minutes break before 1 p.m., okay?
Okay, maybe I will use this opportunity to say also a few words about the memorial session, because on Wednesday evening in Moscow time, we are going to run the memorial session where we will discuss our memories about Dmitry Viktorovich. So maybe those who want to say a few words or show some pictures or something like that, maybe you can contact me and Alexey Klimenko to make the planning slightly easy, to make this part more smooth, because it's always harder to organize the informal things online rather than the real mathematical discussion. Thank you very much.
Yes, you can just write to the conference email and we will filter out all your suggestions. Okay, so we wait until 1 p.m.
1 p.m. Okay.
Could I perhaps ask that you allow me to share my screen in the meantime?
Yes, okay. Let me just take your...
Я выключил камеру.
Just a moment. Okay, so now you can...
Okay, let me try.
Okay, please try.
So what do you see?
I see your slides and everything.
Wonderful, wonderful. But why doesn't it... Do they change?
Yes, yes.
Okay, wonderful. Thank you.
Sí.
Shall I start?
Yes, please. Greetings to everybody. We can now start the first talk of the Anosov Memorial Conference. Our speaker is Omri Sarig from Israel with the title Seen to Everybody. Omri, please, you are welcome.
Thank you very much. First, I'd like to thank the organizers for the invitation to participate in this meeting. I myself, I didn't know Dmitry Anosov. I think I did meet him once. That is to say, I was in the same room with him, but I was a beginning master's student, and of course I didn't dare to say a word to the great historical figure in front of me. Many years later, when I joined Penn State, I heard many stories on Anosov from Yaakov Pesin and from the late Anatol Katok. And they both emphasized repeatedly not just the tremendous intellectual influence he had on them, but also the practical help he gave them at the beginning of their careers. They always said that Anosov used his power in the Soviet system to help and assist beginning mathematicians of talent in the historical period of time that was difficult for many people. So I'm very happy. I was very happy to learn that the Steklov Institute and the Moscow Higher School of Economics decided to hold this event in his honor, and I'm very happy to be able to play a small part in it. I'm going to tell you about joint work with, with Jérôme Bouzy and Sylvain Corvisier. These are my collaborators. And together we studied the properties of Lyapunov exponents of sequences of ergodic invariant probability measures. Now the setup is going to be very simple. We are going to be interested in the action of diffeomorphisms on manifolds. The manifolds will always be surfaces, manifolds of dimension 2, and the diffeomorphisms are always going to be C infinity. We are going to assume that they have infinitely many derivatives. Now, as I said, we'll be interested in Lyapunov exponents of sequences of ergodic invariant measures. Because we are in dimension 2, there are going to be two Lyapunov exponents. The larger one will denote by lambda plus, the smaller one will denote by lambda minus. In fact, all the measures in this talk are going to be ergodic and with positive entropy, and therefore lambda plus will be positive and lambda minus will be negative. Because of
the surface is compact, closed. Surface.
Compact, closed, smooth, everything, connected. Okay, so the starting point for the lecture is the following problem, and that is that in the non-uniformly hyperbolic setup, the Lyapunov exponent does not depend in a continuous way on the measure. That is to say, you can come up with sequences of ergodic invariant measures with an ergodic invariant limit such that the Lyapunov exponents do not converge to the Lyapunov exponents of the limit. Now, Jérôme, Sylvain, and I had a particular problem where we had a particular sequence of measures which converge to the measure of maximal entropy, and we really wanted to know that the Lyapunov exponents of the sequence do converge to the Lyapunov exponents of the limit. And the question that confronted us was, well, how to prove this? And so the question is, what condition do you need to check on a convergent sequence of ergodic invariant measures to be able to deduce that the Lyapunov exponents converge to what they hope they converge to? Well, this is the problem I'm going to talk about today. What condition can you put on a sequence of ergodic invariant probability measures which guarantees that the Lyapunov exponents converges to the Lyapunov exponent of the limit? And here is our result, first in a qualitative form. The result is that if you can check the condition in red, that is to say that the entropy of mu n converges to the entropy of the limiting measure, and the entropy of the limiting measure is positive, then you can indeed deduce that the Lyapunov exponents converge to the Lyapunov exponents of the limit. Again, suppose you have an ergodic sequence of invariant measures, mu sub n, which converges in the weak star topology to an ergodic limit mu. And suppose you can check the extra condition in red, that the entropy of mu n converges to the entropy of the limiting measure, and that the entropy of the limiting measure is positive. Then our result says that you can deduce that the Lyapunov exponents of mu n converges to the Lyapunov exponents of the limiting measure mu. I repeat that we are only asserting this in the case when the diffeomorphism is C infinity and when the dimension of the ambient space is 2, when we are on a surface. This is the qualitative form of our result. Let me now tell you the full form of our result, which is more quantitative in nature. It's an inequality. So again, suppose that you have a sequence of ergodic invariant measures mu n, which converge to an ergodic invariant limit mu. And let's pass to a subsequence so that the limit of the entropies and the limit of the Lyapunov exponents converge. Then we claim that the following inequality holds. So let's look at this together and see what's written here. Consider for the beginning this ratio here. We call this the discontinuity ratio of the Lyapunov exponent. It is the ratio of the limit of the Lyapunov exponents and the Lyapunov exponents of the limit. If this ratio is equal to 1, then the Lyapunov exponent behaves in a continuous way, and we are happy. But if this ratio is not equal to 1, then there is a discontinuity. There is a discrepancy between the Lyapunov exponent of the limit and the limit of the Lyapunov exponents of the terms in the sequence. The further away this ratio is from 1, the bigger is the discontinuity. Similarly, there is a discontinuity ratio for the entropy. If this ratio is equal to 1, then we have continuity. The entropy of the limit is equal to the limit of the entropies. But if the ratio is not equal to 1, then we have a discontinuity. And the further away this ratio is from 1, the bigger is the discontinuity. Now you will notice that...
Omri, may I ask a question? Sorry, apologies.
Sure.
When you say an entropy, you mean topological entropy, right?
No. I mean Kolmogorov-Sinai
Kolmogorov-Sinai metric entropy.
Yes,
Okay.
yes. Kolmogorov-Sinai metric entropy of the measures in question. Okay, you will notice that I'm saying that these ratios are less than or equal to 1. This is an upper semi-continuity statement, which says that if there is a discontinuity, it always goes in one direction. The limit is always bigger. The Lyapunov exponent or the entropy of the limit is always bigger than or equal to the limit of the Lyapunov exponents or the limit of the measures. This upper semi-continuity statement is not our contribution. This was known before. For Lyapunov exponents in dimension 2, it's an exercise. For the entropy, it's a special case of a very famous and very deep theorem of Sheldon-Newhouse that already uses the full force of the C infinity assumption. Our contribution is the middle inequality that says that the discontinuity ratio of the entropy is always at least as far from 1 as the discontinuity ratio of the Lyapunov exponent. In particular, if the discontinuity ratio of the entropy is equal to 1, then the discontinuity ratio of the Lyapunov exponent must also be equal to 1. And this is exactly equivalent to what I said before, that if the entropies converge to the entropy of the limit, then the Lyapunov exponents converge to the Lyapunov exponents of the limit, because if the entropies converge to the entropy of the limit, this is equal to 1. And then by the sandwich rule, this has to be equal to 1, which means the Lyapunov exponents converge to the Lyapunov exponent of the limit. Okay, so this is our result. The rest of the proof is, the rest of the talk is just going to be a sketch of the proof. So if there are any additional questions on the statement, now is a good time. And you must ask directly because I can't see the chat box.
Yes, I have a question. So,
yes, Mira.
Does your theorem can be applied, for example, to a cat map? So I'm assuming that for any dynamical system or operator created by a dynamical system for which the Kolmogorov-Sinai metric entropy is positive, your theorem can be applied. Am I correct to assume that?
It applies for surface diffeomorphisms of class C infinity.
Okay.
That's what it applies to. Already, if you relax it to CR, I cannot really say anything. I mean, I can say something, but not this term. Other questions? Okay, so let me give you a sketch of the proof. The proof consists of 3 main steps. The first 2 are relatively easy, and all of the work is in the 3rd step. So here are the 3 steps of the proof. The first step is to define a numerical quantity, beta, which I'm going to call the density of long neutral blocks, and I will explain to you exactly what neutral blocks are. The second step shows that this parameter beta exactly captures the discontinuity ratio of the Lyapunov exponents. Specifically, the discontinuity ratio of the Lyapunov exponent is 1 minus beta. And the third and most difficult part of the proof is to show that this quantity beta can give you a bound for the discontinuity ratio of the entropy. More specifically, the discontinuity ratio of the entropy is less than or equal to 1 minus beta. So if you combine the last 2 steps, you get that 1 minus beta, 1 minus the density of long neutral blocks, separates the discontinuity ratio of the entropy and the discontinuity ratio of the Lyapunov exponent. And it immediately tells you that this discontinuity ratio is less than or equal than this discontinuity ratio. Okay, so there are 3 steps in the proof. Let me begin with the first step, the definition of this all-important parameter beta. And I'd like to begin with just fixing some notation and reminding you some basics on the theory of Lyapunov exponents. Everything that I'm going to say now is completely elementary, but I'm going to use it all the time, so I don't think it's, I think it may be good to recall it. So we are working in dimension 2. Let's assume that we have an ergodic measure with positive entropy. Then by the Ruel entropy inequality, one Lyapunov exponent is strictly positive and the other Lyapunov exponent is strictly negative. We are in dimension 2, so these are all the Lyapunov exponents. Because we have one strictly positive Lyapunov exponent and one strictly negative Lyapunov exponent, Oscillatet's theorem tells us that at mu almost every point, the tangent space splits into the direct sum of the oscillated spaces. These oscillated spaces change in an equivariant way, and they are one-dimensional. So one-dimensionality is going to be important. What is the connection of these spaces to the Lyapunov exponents? Well, the Lyapunov exponents are nothing other than the exponential rate of growth of the derivative on non-zero elements of these spaces. Okay, so lambda plus is the exponential rate of growth of the derivative on non-zero elements of E plus, and lambda minus is the exponential rate of growth of non-zero vectors in the space E minus. So now, because of one-dimensionality of the oscillated spaces, we have a closed form formula for the Lyapunov exponents. For example, if you look at the top Lyapunov exponent, this by definition is the exponential rate of growth of the derivative on E plus. I can use the chain rule to expand the derivative of f to the power n to the product of derivatives. I don't need to take the product of the full derivative operators. It is sufficient to take the restriction of these operators to the relevant spaces which contain the vectors. These are by equivariance of the action of the derivative, E plus of x, E plus of f of x, and so on. So I can evaluate the derivative of f to the power n in the form of the product of linear spaces on one-dimensional spaces. Linear spaces on one-dimensional spaces act like scalars. Therefore, the norm of the product is the product of the norms. Here I'm using dimension 1, and I can take the log and divide by n and obtain a formula for lambda plus as a limit of ergodic averages. If the measure is ergodic, this limit is nothing other than the integral of the function written there. Okay, so because of one-dimensionality, I have an explicit formula for the Lyapunov exponent. Now, here is a graphical representation of this formula. So what you have here is a graph. The x-axis is n, the number of terms in the ergodic sum. The y-axis is the value of the sum. And what I just told you is that the Lyapunov exponent is the asymptotic slope of this graph. Okay, it's the limit of the ergodic averages, it's the asymptotic slope of this graph. But this is an asymptotic quantity. The fact that in the long term you see asymptotic slope lambda plus doesn't mean that in the short term you see such growth. And indeed, there could be finite periods of time where instead of seeing growth at the speed of lambda plus, you see growth at a much slower pace. Okay, perhaps no larger than a small positive number delta. Maybe you even see decay instead of growth. Of course, this behavior is transient. It doesn't last for infinite amount of time because in the long run you see growth. not decay. But there could be finite pieces of time where you see decay or at least slow growth. These periods of time I'm going to call delta neutral blocks. Specifically, a delta neutral block is going to be a finite piece of orbit where the derivative grows at most like e to the delta k, where delta is a small positive threshold. I remind you that in the long run, you see growth at the rate of e to the lambda plus k, but so everything all these delta neutral blocks, they must be finite for typical orbits, but nevertheless, they may exist. Okay, so now what is the informal definition of this parameter beta that captures the discontinuity ratio of the Lyapunov exponents and bounds the discontinuity ratio of the entropy? It's going to be the density of very long delta neutral blocks along typical orbits for the measures mu I in the limit as I tends to infinity. So obviously there are many, many limits that are hidden in this statement. There is the limit that gives you density. There is the limit that tells you that the length of the blocks you look at tends to infinity. There is the limit that tells you that delta should be taken to be very small, tending to 0. And there is the limit that sends the index of the relevant measure to infinity. There are many, many limits behind this expression. The density of long delta neutral blocks for typical measures from mu I as I tends to infinity. And the question is, what order should you take the limits in? It actually matters, okay? It actually matters. You need to take the limits in the right order. And what I would like to tell you now is what is the right order of taking the limits. So here it is, and that's the formal definition of beta. So again, we have a sequence of measures which converges to an ergodic limit. And let's pick for each measure mu I a typical point xi. Now, what exactly do I mean by typical? I will tell you later. I will have to ask that some ergodic theorem for some function holds for the orbit xi. It will be a full measure condition, which depends on the measure mu I. I will tell you exactly what it is a little bit later, okay? So let's pick a typical point xi, which satisfies this condition that I will tell you later. And for this orbit, let's define the set nu to delta L, which is the collection of all times when the orbit lies inside a delta neutral block of length at most L, okay? So beta is going to be this iterated limit. So this is a long formula, so let's read it together to see that we understand what it means. It's not as bad as it looks. Let's begin from the inside, okay? So what's written here? What's written here is the density of delta L neutral blocks along the orbit of xik, okay? So I take the collection of all delta L neutral blocks along my orbit, I intersect it with 0n, and I divide by n and pass to the limit. Why should such a limit hold? Because it can be expressed as an instant of the ergodic theorem for a suitable function, which I don't want to write down. So if I choose my typical points xi to satisfy this ergodic theorem for this particular function that gives you this density, then the limit inside will exist and it will be a number. This number, of course, will depend on the measure mu I. Because it depends on the measure of mu I, there is no reason for the sequence of numbers that you get to converge as the index of the measure tends to infinity. However, these numbers are always between 0 and 1. So if I pass to a suitable subsequence, the limit of densities will exist. Okay, so I pass to some subsequence of measures for which the sequence of densities written here does indeed converge. And then I know that the second limit, which is the limit where the index of the measure tends to infinity, exists. Now the result is going to be independent of the choice of measure because I sent the index of the measure to infinity, but it will still depend on the parameters delta L, which I use to define the neutral blocks. I remind you, L is a lower bound on the length of the neutral block, and delta is this threshold of maximal possible expansion you allow there. So the limit will depend on delta L. However, what happens when I decrease delta and increase L? If I decrease delta and increase L, I'm making the condition of being in a delta L neutral block stronger. And therefore, I'm decreasing the set nu to delta L. There are fewer neutral blocks with long length and the small threshold delta than there are with short length and big threshold delta. So there is monotonicity in the parameters L and delta, and therefore the last limit exists as well, okay, simply by monotonicity. So when you take the limits in this order, you get a number, beta. Maybe it's 0, maybe not. In the interesting cases, when you have discontinuity of the Lyapunov exponents, it will be non-zero, okay? So this is the parameter delta. Those of you that are familiar with the notion of hyperbolic times will feel this is familiar. This is in some sense a complement of hyperbolic times. These are not times when you have uniform hyperbolicity. These are times when you have a uniform opposite of hyperbolicity. Slow or maybe even slow expansion or maybe even short expansion along the unstable direction.
Hey,
Okay.
Omri, does delta depends on L? Does it converges to 0 in some?
No, it
rate
doesn't
of
matter.
L?
It doesn't matter how you take L to infinity and delta to 0. You can in fact take the infimum because there is monotonicity.
Thank you.
Okay, so we did the first step. We defined this parameter beta. Now we have to show that this parameter beta exactly calculates the discontinuity ratio of lambda plus, and later gives a bound for the discontinuity ratio of the entropy. So let's begin with the easier statement that it exactly calculates the discontinuity ratio of the Lyapunov exponent. So let's return to this picture that exhibits the Lyapunov exponent as the asymptotic slope of the graph of the ergodic sums of this function written here. Now, what is the asymptotic slope? It is the ratio between the vertical displacement and the horizontal displacement. Okay. Now, I claim that the contribution of what happens inside delta neutral blocks doesn't really affect much the vertical displacement. And the reason is that if you take the maximal delta neutral blocks, then at the very last step, things almost cancel out. If you think about it, you will see that this is true. For this reason, the effect of delta L neutral blocks on the value of the sum can be bounded in terms of delta and L. It's negligible. So when you calculate the vertical displacement, this sum, you can ignore all terms in the sum that comes from delta L neutral blocks. They do not affect the vertical displacement much. However, they definitely affect the horizontal displacement simply because they waste time. Okay, so this is, if you wish, the picture. The neutral blocks do not affect the total sum up in a non-negligible way, but they do affect what you need to divide by because they waste time. Okay, so armed with this intuition, we can write down this approximate formula for the Lyapunov exponents of mu n. It is the limit of the ergodic averages of this function written here, but in these sums you can remove the terms coming from neutral blocks. They don't affect the sum much. Okay, they only contribute something up to an error which is negligible if delta is small and L is big. Okay, so now if we want to calculate the limit of lambda plus mu n, we need to calculate the limit of this expression, the limit of these averages with the terms coming from delta L neutral blocks removed. Now, the trick to do this is to calculate something a little bit more complicated. What we're going to do is we are going to view these averages of numbers as the integrals of a function with respect to an empirical measure. And this is the empirical measure that is written here. It is a little bit confusing because it's not an empirical measure on the manifold. It's an empirical measure on the projective bundle of the manifold. That is to say, the collection of pairs where the first coordinate is a point and the second coordinate is a direction, tangent direction to the manifold. Okay, if you integrate the function log of the norm of the derivative restricted to a direction with respect to this empirical measure, you will get exactly this sum. So instead of calculating the limit of these numerical quantities, we are actually calculating the Week-Star limit of these empirical measures on the projective manifold, on the space of pairs where the first coordinate is the point and the second coordinate is a tangent direction. And there is a technical lemma, not difficult. If I had 10 more minutes, I would have been able to give you the proof. There is a technical lemma, not very difficult, that says that this limit exists, and it always takes the form 1 minus beta times a measure. And what is this measure? It's the lift of the limiting measure to the graph of the top oscillated space. Okay, the graph of the top oscillated space is the collection of points where the first coordinate is a point and the second coordinate is the oscillated direction. Okay, now I do like to explain to you why 1 minus beta appears here. Okay, because this is very easy. 1 minus beta is simply the total mass of the right-hand side. What is the total mass of this limit? Well, if you calculate the total mass of this limit, you will exactly get 1 minus the limit we had before, which defined beta. Okay, it's exactly the same iterated limit. Okay, this is why what you get here is 1 minus beta times some measure, and we actually know what this measure is. It is the lift of the limiting measure to the graph of the top oscillated space. So now we are done, because it's just a matter of unfolding definitions to see that the limit of this expression as n tends to infinity is, okay, you have to take the limit of the term on the right-hand side as delta tends to 0 and n tends to infinity, and n tends to infinity. And this is exactly this limit here. So it's 1 minus beta the integral with respect to this measure of the function that produces this sum from this empirical measure, this function is just this, what's written here. It's the log of the norm of the derivative restricted to a direction. And because the limiting measure mu hat plus is the lift of the limiting measure to the graph of the oscillated space, this integral is exactly this integral, this time on M, with respect to this integrand. This, because of ergodicity, is the limit of the ergodic averages, which I showed you before is the top Lyapunov exponent. So you get that the limit of lambda plus of mu n is just 1 minus beta times lambda plus of the limiting measure. So we did the second step, okay? The asymptotic density of long neutral blocks calculates the discontinuity ratio of the Lyapunov exponents, and you see that it's not very difficult. And now we come to the main step of the proof. Okay, the main step of the proof, which is to use the density of neutral blocks to get an upper bound for the discontinuity ratio of the entropy. Okay, and that's where all the hard work goes into. And I have to apologize that I don't have time to show you the proof of this. I would need more than an hour for this, maybe even 2 hours. But what I do think I can do, and I will try to do, is to give you a flavor of the argument and explain to you at least what goes into the proof of this statement. Okay, so basically what I would like to explain is what is the connection between neutral blocks and entropy. Okay, that's what I will try to explain to you. And to do this, let's recall several standard ways for bounding the entropy of an ergodic invariant measure. So let's begin with a very classical method called the Katoch's entropy formula. It works for all homeomorphisms on compact metric spaces. And it says the following thing: if you have an ergodic invariant measure, then you can bound the entropy of the measure by counting how many n epsilon Bohren balls you need to cover a set with measure at least 1/2. Okay, so you look at the smallest possible collection of n epsilon Bohren balls whose total mass is at least 1/2. This number grows exponentially, and the exponential rate of growth gives you an upper bound for the entropy. If you send epsilon to 0, it will actually give you a formula for the entropy. That's Katoch's entropy formula. Notice that in our case, when we have a diffeomorphism on a surface, this formula talks about covering a two-dimensional set, a subset of a manifold, by other two-dimensional sets, which are n epsilon Bohren balls. Okay? Now, what I'm going to do next is show you 2 other methods for bounding the entropy, which use one-dimensional objects. That's easier to do. And the first one is the Ledrapier-Young theory. So let's now assume that we are smooth, that we have a diffeomorphism, at least class C2. Then a very rudimentary form of Ledrapier-Young theory tells you that instead of covering a two-dimensional subset of the manifold with measure at least 1/2, you can cover a one-dimensional subset of a one-dimensional local unstable manifold with conditional measure at least 1/2. Okay, the Ledrapier-Young theory implies that you can bound the entropy by the exponential rate of growth of covers by n epsilon balls of pieces of local unstable manifolds of typical points with conditional measure at least 1/2. So we reduced one dimension. Now we are not covering the two-dimensional subset of the manifold with respect to the two-dimensional measure. Now we are covering a one-dimensional subset of the manifold, a piece of an unstable manifold, with respect to a one-dimensional measure, a conditional measure. But the sets we're using for the cover are still two-dimensional. They are still n epsilon Bohren balls. So the third method, which is Yomdin theory, gives you another improvement. Now you need to assume more smoothness. You need to assume C infinity. And in this case, Yomdin theory tells you that you can bound the entropy from above by looking at exponential rate of growth of a one-dimensional object, the local unstable manifold of a point. Instead of calculating the complexity by looking at covers by two-dimensional pieces and epsilon Bohren balls, you can calculate the complexity by looking at covers of one-dimensional pieces of the local unstable manifold. So finally, we arrive at a situation where we are covering a one-dimensional object, the local unstable manifold, by one-dimensional pieces of this manifold. Okay, so let me say a little bit more about exactly what covers we are going to look at. So here is not really an introduction to Yomdin theory, but an introduction to an introduction to Yomdin theory. It's really very, very elementary what I'm going to say. Yomdin theory begins with a way to quantify the complexity of a CR object. Now it works in any dimension, but for the sake of explanation, I'm going to restrict to dimension 1. So let's talk about a CR curve, okay, a one-dimensional CR object, a CR curve. How does Yomdin measure the CR complexity of this curve? Well, the idea is that you look at the minimal number of parameterized pieces of the curve, which are modeled on the unit interval and have CR size less than or equal to 1, which are needed to cover the curve. Let me say this again. You look at the minimal number of CR curves modeled on the unit interval with CR norm less than 1 that you need to cover the curve. So for example, look at this picture here, okay? You see this blue curve here. So you see that it has two sharp bends, okay? Now in these bends, the direction of the curve changes dramatically. So it's very difficult to find the parameterization of the bend with small C2 norm because the first derivative will always have to have a jump because the direction of the curve changes. The only way to do this is to dissect the curve into very, very fine pieces close to the bends so that firstly, the first derivative or maybe higher order derivatives, if you're looking at CR size, do not change much along each of the small pieces. And secondly, you parameterize each small piece using a parameterization model on the unit interval. This basically means that you move extremely slowly along each of these small pieces. And then you have a chance of getting small CR norm, okay? So this approach of measuring the CR size of an object by looking at reparameterizations with bounded CR norm basically amounts to looking at your objects and at places where some higher derivative, maybe first derivative, maybe second derivative, maybe third derivative, places where this has an abrupt change, you cut it into very, very fine pieces. And the minimal number of pieces you need will give you the CR size of the curve. Okay, so how do you connect all this to entropy? Well, this is very classical. It already appears in the work of Yomdin, but in the work of Newhouse from I think 1980 or something like this. And the way to do it, I mean, you can do it using Lederer-Young. So let me explain this. So let's assume that you have a surface diffeomorphism, smooth, and you have an ergodic invariant hyperbolic measure. And let's pick a local unstable manifold of a typical point with respect to the measure, and let μx be the conditional measure for this typical measure. So the entropy estimate says that the entropy of the measure can be bounded by the exponential rate of growth of the smallest possible family of covers of the local unstable manifold by a family of curves, okay, which covers it, and which has controlled CR norm, not just of the curve, but also the iterates of the curve. Okay. So again, please look at the formula in red here. The entropy of an ergodic measure is bounded above by the exponential rate of growth of a cover of the curve by CR parameterized pieces of the curve, which satisfy a certain control, CR control of their norms and the norms of their images under iterates of the map. You don't need to take all iterates of the map. It is sufficient to take a subset of iterates with bounded gaps, but let's ignore this for the moment, okay? For simplicity, imagine that we are taking bounds on all iterates. That's not far from the truth. So what does this bound that is written here, what does it say and why is it tied to entropy? It's actually very simple, okay? Imagine that you have one of those pieces that we use in this reparameterization. So this is a parameterized curve modeled on the unit interval, which satisfies a CR bound on its images, okay? Now let's imagine that this bound holds not just for a subset of iterates, but for all iterates, okay? Then what does it say, this bound? It says that sigma I, f of sigma I, f squared of sigma I, f cubed of sigma I, and so on, they all have CR norm less than or equal to epsilon. Well, if they have CR norm less than or equal to epsilon, they have C1 norm less than or equal to epsilon. If they have C1 norm less than or equal to epsilon, their length is less than epsilon, because the length of a curve is the integral of the norm of the derivative on the domain, and the domain is the unit interval, okay? So each of these pieces has length less than or equal to epsilon. So now let's pick an arbitrary point x on sigma I. Well, if x is on sigma I, then f of x is on f of sigma I, and f squared of x is on f squared of sigma I, and so on. If the length of each of these pieces is bounded by epsilon, then each of these pieces lies inside an epsilon ball around the corresponding point. For example, f squared of sigma I will be inside an epsilon ball around f squared of x. In other words, sigma I must lie inside an n epsilon ball. So what I'm telling you is that once you have a family of CR curves which satisfy these bounds, then it automatically generates a cover of the curve by n epsilon balls. Okay? I'm sorry, any questions? I heard some question.
No, someone has to mute herself.
Oh, okay. So again, if you have a family of pieces which covers the local unstable manifold and satisfies these bounds, then it lies inside an n epsilon ball, and therefore you automatically get a cover by n epsilon balls. And now you can invoke the Drapier-Yang theory, a very rudimentary form of the Drapier-Yang theory, and obtain a bound for the entropy. Okay? This is how Yomdin theory and entropy theory play together. So the result of all this is that if we want to prove the third step, which is written here, what we need to do is we need to find efficient covers of a local unstable manifold by pieces with bounds on their CR norms. Specifically, what we do is we find families of parametrizations whose exponential rate of growth is bounded by this expression here. This is the main term, okay, 1 minus beta entropy, which is what we aim for. But I have to tell you that we also have an error term which has this form. R here is the number of derivatives that you use. It's a typical Yomdin theoretic error term. It will not be a problem for us because in our case we are C infinity, so we can take R to be as small as we wish. But this is what we do. We build these families of reparametrizations. So now you have to ask, where do neutral blocks enter? So now I'm going to wave my hands vigorously and try to explain to you where neutral blocks enter. What I'm going to say now is going to be very, very imprecise, but it has a grain of truth in it, okay? The difficulty is to turn this grain of truth into a rigorous proof. So I'm going to lie to you now, but not completely. Okay, so how do you construct the families of reparametrizations which satisfy bounds on the CR norms on iterates, okay? Well, you start from your curve. Let's say that this is a piece of an unstable manifold that you want to cover. I want to cover it by pieces with CR norm less than or equal to epsilon. In particular, they need to have short lengths at most epsilon. Maybe my piece has length bigger than epsilon. So I have to chop it to smaller pieces so that each piece has a CR size less than epsilon, and then I can satisfy the CR norm on the zeroth iterate. Now I want to take care of the CR bound on the first iterate, so I apply the map. Now, because I'm talking about sub-curves of the local unstable manifold, things are going to stretch. So what was short enough at time 0 may not be short enough at time 1. So because of stretching, I need to divide and then pull back the partition to the original curve, and this will give me the second family of reparametrizations. Now, because we are on a compact manifold, eventually bands have to develop. Now, bands are very interesting in this theory because they are the places where higher derivatives start to create problems. If you have a band and the curvature is big, okay, so the first derivative is big. Maybe you have more subtle bands when the third derivative is the one that causes you the problems. Okay, maybe the curvature is what changes abruptly. But anyway, at places where you have bands, you need to partition very finely, as I explained to you before, to be able to have pieces with which have CR parametrizations of norm less than epsilon. And then you pull back this partition to the original curve, and you get a finer partition. Notice that you get very fine partition at parts of the curve which eventually map to bands. And you continue in this way, okay? So now let's see what happens, okay? Let's imagine that we are trying to apply this algorithm to a piece of the curve in a neighborhood of a point which eventually enters a neutral block. I remind you, a neutral block is a place where instead of expansion at the rate of lambda plus, that is the asymptotic reality, you see for a short period of time a very weak expansion, or maybe you even see contraction rather than expansion. This is a neutral block. So what happens? So as long as you're outside the neutral block, the main effect which determines the growth in the family of parametrizations is going to be expansion. And then the family of parametrization grows in an entropic rate as predicted by the Drapier-Yang theory. Okay, so when you're outside neutral block, the asymptotic rate, the asymptotic rate of exponential growth of the family of parameterizations is roughly the entropy, basically because of the Drapier-Young. But when you enter a neutral block, stretching stops, okay, or at least it's slowed down considerably. It doesn't mean that you don't need to increase your parameterization because you can still develop bands. You can develop bands without stretching. However, it's the bending that is going to be the dominant mechanism which increases your sequence of parameterizations. At this part of the time, it's Yomdin theory that begins to play the important part. Yomdin theory basically says in a very, very rough way that if you have a very, very smooth map, it cannot create many bends on a smooth curve. Because bends imply that some higher derivative must be big. Okay, so Yomdin theory. So at this part of the time, we invoke Drapier-Young theory to control the exponential rate of growth of the family of parameterizations. And during neutral blocks, we invoke Yomdin theory, which gives you very effective tools for bounding the exponential rate of parameterization due to bends. Now, when you combine the two arguments and you see, and you monitor the rate of growth of the family of parameterizations in time, you see that, as I said, outside neutral blocks, Drapier-Young theory gives you exponential rate roughly the entropy, but inside neutral blocks, the bound comes from Yomdin theory, which is much weaker. Okay, the higher than the R, the higher the number of derivatives, the slower is this growth. When you combine the two things together, you get that the exponential rate of growth of the family of parameterizations is 1 minus beta times the entropy. That's the contribution of complements of neutral blocks. You have 1 minus beta because beta is the frequency of neutral blocks, of frequency of times inside neutral blocks. And then you have beta times the Yomdin estimate of rate of growth, which tells you what happens inside neutral blocks. Yomdin theory has an entropy estimate which is inversely proportional to R, the number of derivatives. We don't worry about this because we have a C-infinity map, so we can take R to be as big as we wish, and therefore this becomes negligible, which leads us finally to the bound that we are interested in. Okay, so this is the approach that we use to prove the third step of the proof, written here, that tells you that beta, the asymptotic density of neutral blocks, can be used to control the discontinuity ratio for the entropy. Okay, so here is a summary of the argument. You define a number beta, which is roughly the asymptotic density of neutral blocks. You show that this number exactly calculates the discontinuity ratio of the Lyapunov exponent. You show using Yomdin theory that it gives you a bound for the discontinuity ratio of the entropy. And then you deduce immediately that the discontinuity ratio of the entropy, since it's bounded by 1 minus beta, has to be smaller than the discontinuity ratio of the Lyapunov exponent, which is equal to 1 minus beta. So that is that proves the result. And with this, I will thank you and finish.
Thank you. Are there any questions or comments?
I have a question.
Please.
Do I understand correctly that the fact that you talk about two-dimensional manifold comes actually from the use of Drapier-Young theory?
No, Drapier-Young theory and Yomdin theory both apply to higher dimensional cases. The place where I use one dimensionality very, very powerfully is in expressing the Lyapunov exponent in terms of an additive cocycle, the derivative cocycle. In higher dimension, it is a sub-additive cocycle.
Yes.
And then my first step, my second step, which relates beta to the discontinuity ratio of the Lyapunov exponent, is no longer valid.
So is that the artifact of the proof, or you think this is somehow harsh truth of law that in higher dimension it will simply build not true?
Okay, so the truth is, certainly it's an artifact of the proof. There is a question, what is the right statement in higher dimension? We didn't work on it, and the reason is that what I told you today is not really a theorem, it's a lemma for something else, which doesn't work for other reasons in higher dimension. So we didn't really try to do this in higher dimension.
Thank you.
No problem.
Any other questions? No questions, no comments. So let us thank the speaker.
Thank you.
For a beautiful talk. And we have a break until 2 p.m.
Excuse me. Hello.
Hello, hello.
Hello, how are you?
Good. How are you, Bassam?
I'm fine. And you? How is everything?
Thank you very much. I'm fine.
I heard you had COVID at some moment.
It was 4 months ago, and it was rather hard, but now I am recovered completely. Thank you.
Quite okay. Tell me, you said there is a break until 2? I don't understand. I thought my talk was like at noon or something. What is?
Well, 2 Moscow time. We now have 1 p.m. and 45. And in 15 minutes, you start your talk.
Okay, okay. Thank you. Sorry, I misunderstood. Fine, because I thought you canceled my talk because I told Sasha I had some.
No. Bassam, you can share your screen. Please try to do this.
No, wait, I need to connect my iPad.
Okay.
Mm-hmm.
Yeah.
Привет.
Alexei. But you can go for your break. Don't worry about me.
Well, so see you soon before the beginning of your talk.
Okay, thanks. Okay, now Zoom link. So I need to register also for this one. No, nom d'affichage. Non d'affichage. No, 1 second. Okay. I'm not a host. So if you could add my iPad.
Is it also named Bassam Fayad?
It is named maybe Rahif or I don't know. Yeah, Bassam Fayad, yeah.
Just a moment.
By the way, I could.
I see. Okay. Well, here we are.
And now I can share my screen. Okay. So which working. It's okay?
Yes, everything is fine.
Okay, perfect. Thanks. So we take the break 5 minutes, right?
13 minutes, as far as I know. Oh, no. Yes, 12.
Yes. Okay, thanks. See you.
Yeah.
Bye. Thanks, Alexei.
Riversiamo.
Привет, привет.
Привет.
Как дела? Оль, хорошо?
Привет, привет. Леша, привет.
Big confusion with time. I thought my talk was at 4. So in fact, I missed 4 hours delay. I mean, they made this very nice schedule with all time zones.
Привет.
But it had a counter effect on me. I got confused.
Okay.
Anyway, so it's going to be a bit improvised.
Юлия Сергеевна. Здрасте, Юлия Сергеевна.
Здравствуйте, Машенька.
Леш, привет.
Маша.
Здравствуйте, Даниэла.
Здравствуйте, здравствуйте.
Здравствуйте.
Долго вас не видела, да.
Здравствуйте.
Юлик, добрый день.
Здравствуйте.
Сергей Пелюгин.
Здравствуйте.
Лиса.
Не понял, слышит он меня или нет? Юлик, слышишь меня, нет?
У меня иногда отключается звук. Сейчас слышу.
Ага. Добрый день.
О, здравствуйте.
Очень рад видеть.
Лёша.
Здрасте.
Как здорово, что здесь сегодня мы собрались. Да.
Оля,
Да.
давно вас не видел.
Здравствуйте, Сергей Юрьевич. И я вас взаимно.
Очень приятно.
Спасибо.
Здравствуй, Юлик.
Здравствуй, Слава.
Да, это здорово. Странно, конечно. Никак не наладится.
Да, так естественно все-таки встречать друг друга и пожимать руки,
Да не
и толпиться у
говори.
одной доски.
Да, совсем другое дело.
Да, да, да.
Ну, не знаю.
Сейчас уже все тут общались, это самое, нет сил, как? А так сидят, молчат, каждый за своим экраном, ну так, по основному.
Да, да, да.
Поводов для общения масса. Вячеслав Кузьмович,
Ай, да.
вам не приду. Ладно, не обидитесь.
Это когда будет? В среду-то?
В среду, да.
Ну, не приходи. Ты...
Ну, правда, после этого мы решили семинар не отменять, а то уже его и так 3 недели уже не было.
А, так решили не отменять семинар?
Нет, ну какой? Вот этот обучающий семинар. Нет, который мой в среду, по среду, с детьми.
А, ну это
Да.
твои дела.
Нет, тут-то я сказал, что я не буду докладывать на этой неделе. Я не знаю, отменит они, не отменит. Посмотрим.
Нет, ну как, ну надо отменить, а то что не...
Нет, ну меня не будет, ну, может быть, они кого-то другого там хотят послушать, не знаю.
Да не, мне кажется, надо нам это договориться с Тураевым. Нет, нет,
Я
надо...
написала, и Леша написала, и Дине Тураеву, что я не буду, я хочу доклады послушать на конференции.
Ну, не так пишешь. Надо сказать, что надо отменить, потому что многие же хотят послушать. Ну, конференции-то все-таки
И
конференция.
отправила, ну вот вы видели, пришло по рассылке по нашей этой, я сказала, Леша попросила отправить, он всем должен был отправить, и он это сделал.
Кого отправить? Чего отправить?
Рассылку по этому семинару вот, по Аносову. Она была
Ну да, нет, это вот хорошо было сделано. Мне кажется, что надо давай с Димой договорись.
Хорошо, чтобы просто отменили.
Что за проблема? Мы в праздник собрались.
Да,
Зато...
перевыполнили план, да.
Ну да, ну я думаю, что это ни к чему. Ну чего уж тут.
Bassam, did you try to share your screen with us?
Yes, yes.
Yes, it is already shared. It will be just a whiteboard.
Ah, it is just a whiteboard. Okay, okay, okay.
For example.
Ага, привет. Привет, окей.
I should say.
Okay. 1 minute left.
Viva everything. Okay.
А где у нас Сережа Пелюгин подевался? Поздоровался, и я думал, он еще пару слов. Сереж!
Здесь я, здесь.
Я просто хотел еще на тебя взглянуть разок, спросить, как у вас дела там в Петербурге.
Да, более-менее нормально, но вот...
Что-то мне хотелось, и что-то такое...
Dear friends, it's time to start.
Okay.
Okay.
We will have time
we will have time after the talk, a lot of it. So now we have a next talk by Bassam Fayyad, Michael Breen professor at Maryland. Please, Bassam, start.
Thank you very much. Thanks for the invitation. Spasiba. The man, Anosov, I met him the first time in Trieste. I was a student and he gave a talk, and it was impressive because he put one transparent and it was handwritten transparent. And then he stood in front of the big screen and in front of the crowd, and he gave a speech of 1 hour, non-stop sentences, and never looked back at his transparent, never went to the board, was just standing up and delivering a speech, a huge speech. And it was impressive, and it was in Russian. So somebody was translating, I think. And then I met him much later in the institute in Moscow, and it was quite nice. He came to my seminars, and he was extremely sound and precise, and asked very, very deep questions. And when my time went out, and I always take more time than my time, I think, and this like bad habit. And then he looked at the audience and said, this is a Moscow seminar, so he can speak as much as he wants. And then he asked me many questions after the talk was over, and I didn't have time to send him an email and say, react on his questions. It was about KM theory and also the counter KM theory that is of which the basic tool is the Anosov-Katok method. And he was aware of all the progress going on in the both fields, and his questions was extremely thought-provoking, and I wanted to write to him and to interact, but he passed out. And so here we are now celebrating a second conference in his honor, and I am honored to be here. I'm going to talk about a subject that we were working on for a while with my nice collaborators, Daniela Damjanovic and Masha Saprikina, who are in Stockholm. So what is the subject? The subject is rigidity of affine actions on the torus. So you give yourself a homomorphism from ZK to SLN, SLD, Z. So what does it mean? It means like you give yourself K commuting matrices, okay? So let's put K equal to 2 for our, when we illustrate. So you give 2 matrices, AB equal BA. And then you consider commuting affine action where A is equal to A plus alpha and B is equal to B plus beta. K can be 1, so this is just like one matrix, but for the moment, we illustrate with K equal to 2 because this is the main. And then the main question is you perturb into, you perturb your action into homomorphism in the group of volume preserving diffeomorphisms of TD. So of course the action AB, you see the action rho of 0, 1 is A, and rho of 1, 0 is B. and rho of KL is AKBL. So rho is acting by affine matrices on TD, okay? And you perturb it into an action by diffeomorphisms of TD. And the question is, when is rho rigid? Rigid means when you perturb it, is it C infinity conjugated to itself? The question goes back to works by, I mean, at least in this context of affine maps on the torus by and abelian actions to Spatsier, Katok, and many people who developed the theory, and with a theory that is extremely thriving in the case where there is hyperbolicity in the pair AB, but we will be interested in the case where there is no hyperbolicity at all in the pair AB.
Bassam, repeat please, what does it mean that rho is rigid?
Okay, so rho is rigid means that if rho tilde is close to rho in some CR and R is sufficiently big, and rho tilde is smooth, then rho tilde is C infinity conjugated to rho, which means there exists a conjugacy H that conjugates all the generators of rho tilde to small a and small b.
Okay, thank you. Mm-hmm.
So this means like there exists H such that HA, H inverse equals rho tilde of 0, 1, and rho tilde of 1, 0 is equal to HB, H inverse. And H is infinity. Yes? We will give a different, another definition of rigidity, because in our setting where there is no hyperbolicity at all, we cannot have a so strong rigidity statement. And it will be, all this will be very clear. So let me now talk about the case, say, K equal to 1. This Z actions. So it is famous that Z actions, when A hyperbolic, right? Hyperbolic matrix, then hold stability only, right? So this is Anosova theorem. That's the man's theorem. If A is hyperbolic, there exists a structural stability with the directions of A surviving up to Holder conjugacy, and not just the directions, but also all the decomposition, stable, unstable manifolds, and structure and local structure product and local product structure. And there is a conjugacy, in fact, between the nonlinear and the linear. Okay. Then this structural stability can be upgraded to smooth structural stability or rigidity as defined here if periodic data match, then possibly you can see infinity rigidity. This is a theory that is developing a lot. It's based on Lifshitz cohomological stability theory. And in the case of dimension 3, it has been solved by Gogolev and, wait a second. Yeah, I'm going to forget names here. Okay, Gogolev is here, and Federico will talk about the subject. So you will have all information you want about stability modulo periodic data. It's not my concern here. I just wanted to say that there is some kind of smooth rigidity even for Z actions if you accept an infinite dimensional, an infinite number of moduli for rigidity. So there exists modulo an infinite number, a countable number of moduli. These periodic data are invariants of C1 conjugacy. And if they match between the nonlinear perturbation and the map A, then you get C infinity rigidity. It is a field that is very active, and there is difference between when you take a linear hyperbolic and you perturb it, or you perturb hyperbolic hyperbolic Anosov map at large. Okay, so I'm not going to enter in these details. I'm going to say there is another kind of rigidity when k is equal to 1 and A is identity. And here you get the Km rigidity. So what is this Km rigidity? Km rigidity tells you if you take the map A equals identity plus alpha. Yes, and if you perturb it into identity plus alpha plus delta F. And if you suppose delta F small in some CR norm, and if you suppose alpha Diophantine, and Diophantine means badly approximable by rationals like K alpha plus L bigger than gamma over K to some power for all K and all L, for all K in ZD and all L in Z, well, star, somebody is in star here, cannot be 0K. If you have this and, and so this is F tilde, right? And F tilde preserves volume. And integral of delta F d mu equal to 0, then F tilde is infinitely conjugated to A. This is the famous Arnold theorem, Kn theorem. Yes, so I repeat, maybe you don't know it under this form, you know it with conjugacy modulo translation, but this translation that corrects the rotation number vanishes a posteriori in under the condition that the integral with respect to some invariant measure is alpha. I can say it differently. I can say that F tilde sees alpha in its rotation set. Okay, and this means that modulo seeing the rotation number and modulo the fact that the rotation vector is Diophantine, you have a smooth conjugacy. We call this Km rigidity. So let me give this definition as a fast definition. It works also for an action. So a rho given by an affine action. Affine action rho is Km rigid. So that's a definition that is useful. Affine action rho is Km rigid if rho tilde equals rho plus delta F. So here delta F, you must imagine it's delta F1, delta F2, delta F3, up to delta Fk, because rho is K dimension. action. Yes. So if delta F integral equal to 0, and this is volume preserving. So we consider volume preserving perturbations. We suppose that the perturbation, the nonlinearity, has 0 integral. Okay, it doesn't mean much a priori, because rotation number and rotation vector and rotation set for a parabolic or for a hyperbolic or for any affine action on the torus is not well defined. Okay, these numbers alpha and beta, for example, they can vary under conjugacy. You can conjugate with something volume preserving, a pair AB, and get different alpha and beta. They are not moduli of C1 conjugacy. So anyway, we say if the integral is 0, and this will correspond to seeing the rotation vectors in your nonlinear action. Then rho is plus delta F small, and some CR known, plus Diophantine condition on affine part of rho, full measure Diophantine condition, plus full measure, plus full measure condition on affine part of rho. Then rho tilde is C infinity conjugate to rho.
Is this action on a torus?
Yes, but you can, okay, my setting is affine actions on the torus. They are matrices A plus alpha, B plus beta, okay? And the condition here is that I modify A plus delta F plus alpha, right? B plus beta plus delta G. I suppose they commute. I suppose volume preserved by these maps. Yes, each one. We suppose the integral of delta F and delta G is 0. We suppose delta F and delta G small, and we get conjugacy to A plus alpha, B plus beta. This is, if this holds for almost every alpha beta, we call the affine action Km rigid. Exactly like identity is rigid on the circle, or identity is rigid on T2. You know, when you take a circle diffeomorphism, that is a perturbation of identity, you look at its rotation number. If the rotation number is Diophantine, and if smallness is adequate with the Diophantine condition, you are C infinity conjugate to the rotation. We generalize this definition to pairs of matrices. And we ask the question, when is a pair of matrices rigid? And if it is not, when is it Km rigid? And can you classify all pairs of matrices? So you give yourself a pair of commuting matrices on the torus, and you ask the question, how can you perturb it? How can you get a nonlinear action nearby? What are your possibilities?
So you mentioned a affine part, the affine condition on a affine part of rho. So rho is affine. What is affine part? Is it alpha?
Yes, exactly. It's alpha and beta. A and B are just matrices in SL and Z. So the condition is on alpha and beta. You will see my theorem, it will be very clear. Okay. Let's agree that this definition is maybe a bit vague, because I wanted to convey the idea that under this kind of definition, and very counterintuitively, you may say, identity is a rigid map. Okay. identity as when you make it affine, it becomes rigid. Here, for example, if A equal B equal identity, then you get Moser's KM theorem for commuting Diophantine translations. Okay, so Moser's theorem, I can state it with my definition by saying identity, which is Z2 action on the torus TD, is Km rigid. Okay, Moser did it for circle actions. It was generalized, I think, by a student by Boris, a student of Daniela. Okay, what do we want to do? We want to make a statement. Okay, we want to make a statement. We want to analyze what happens for a pair of matrices. And so we go to, so K equal to 1, I repeat, I know two cases of rigidity. One is when the matrix is hyperbolic and when I have infinitely many periodic data that code for the rigidity, for the smooth rigidity. And when K equal to 1 and A is identity, we have Km rigidity if we add the constraint of preserving a Diophantine condition. Okay? When A is parabolic, for example, x plus alpha, x plus y, you see that you have no chance of rigidity in either sense. Why? Because you do x plus alpha plus phi of x plus y, x plus y. You take phi that preserves, has integral 0. This perturbation will satisfy all the conditions of the Km perturbation-like thing. It preserves area. It has preserved alpha. And you take alpha Diophantine, and nevertheless, this will not be conjugated to x plus alpha, x plus 1. So parabolic actions will not be Km rigid. And the only Km rigid on K equal to 1, at least for tori, is identity. Okay? I mean, here you may invoke the theory of stability of parabolic maps, and you have a countable number of obstructions. And if they do vanish for the nonlinear perturbation, you can smoothly conjugate to the linear model. But you have something like this, like infinitely many periodic data. Here you have infinitely many distributions that have to vanish for the nonlinear perturbation in order to get a conjugacy. Moreover, this is Katok. Katok studied the cohomological equation. So Katok showed that cohomological equation above T alpha or S alpha, because this is Q product, above S alpha is tame stable. Tame stable means if you have a function, so you have a function, say h of S alpha minus h equals delta f. If delta f is small, if it has a solution, so if the countable number of distributions on delta f vanish, then there is a solution h, and this solution is tame, which means that the solution, if it exists, if h exists, then h in CR is comparable to delta f in CR plus tau, provided alpha is in DC and DC tau here. Okay. However, for higher step parabolic. So for example, take S alpha equal x plus alpha, x plus y, y plus z. So this is on T3, huh? And alpha Diophantine. Then the cohomological equation HS alpha minus H equal delta F is not stable. What do we mean? We mean it is stable if there is a solution, and if delta F is smooth, the solution H is smooth. But H in norm CR will be comparable to delta F in norm C2R plus tau. This was kind of overlooked by Katok, who said that the theory is the same for both. In a sense, it's correct. The theory is the same because there is countably many distributions, and I'm going to tell you what are these distributions. And when the distributions vanish, there exists a solution, and the solution is as smooth as the function. So the transfer function is smooth if the function is smooth. But the main difference between step 2 and higher step is that in higher step, you lose a lot of derivatives. While in step 2, you don't lose derivatives. You see here R. People who want to do KM theory, they know that losing 2R, losing so much derivatives is very bad. For example, this allowed us with Daniela and Masha to produce, using Anosov-Katok method, to produce the following example. So you take alpha DC, no matter what is alpha, if it's Liouville, it's even better, and you produce F that is equal to S alpha plus delta F. Delta F is volume preserving. And such that delta F is small in norm C2R, but F is equal to H S alpha H inverse with H only CR plus 1, or at not so. Okay, so H is CR, but not CR plus 2, say. What do I mean by this is that we showed that there is no chance that any KM rigidity holds for step 3 action, for step 3 Z action, even if you add infinitely many moduli. You see, with our perturbation, we do have a conjugacy, but the conjugacy is not C infinity. I mean, there is well, here the example is not C infinity. F is not C infinity. That's the we wish to that. I mean, we believe that one should be able to construct F smooth that is not more than, say, C1 conjugated to S alpha. But for the moment, what we can do is construct F that is C2R close to S alpha, is C2R, but is not more than CR conjugated. So this shows that KM theory here is not working. Okay. Let's now forget about Z actions and go to higher rank actions, and remember what is the theory and what are the theorems that we are going to prove. Okay. k bigger or equal than 2. So what do we know? So there is a celebrated theorem by Katok and Daniela, and Katok, that says the following: if rho, okay, so if the linear part, so remember we have an affine action here and we want to make difference between affine part and linear part. So let me say if A, B, this is a commuting pair of matrices on TD. So here, my standing assumption from now on is I have a pair of commuting matrices in SLDZ. If AB is higher rank, then AB, which is commuting action A plus alpha. So standing assumption, AB equals BA and A equals A plus alpha, B equals B plus beta, commute. Okay, if AB is high rank, then AB is C infinity rigid. It means that, so let me comment on this. What do we mean? What is high rank? AB is high rank if you take any AKBL with KL different from 0, ergodic. For any KL, not 0, 0. This is equivalent to saying that AKBL is a partially hyperbolic automorphism of the torus, irreducible. And you know that these irreducible partially hyperbolic automorphisms are ergodic. And they are partially hyperbolic. It means they do have stable and unstable directions. And the consequence, as shown by Daniela and Anatole, is that if you perturb small a, small b in sufficiently high regularity, the action AB will be smoothly conjugated to the perturbation will be smoothly conjugated to AB. Yes, so for any F close to A in some norm sufficiently high, and G close to B, and FG equals GF, then F is equal to HA, H inverse, and G is equal to HB, H inverse. So this is rigidity in the strong sense without assumption of volume preserving and without assumption of preserving any data. Okay. Now you wish to go, so this is called the higher rigidity, higher rank rigidity, and it has other manifestations in other settings for higher, for much bigger groups that act like bigger than ZK, suppose like SLNZ. Rigidity of affine actions was proven by Fisher and Margulis, and rigidity of actions in a global setting, not even near the commuting the affine maps, is now an active subject with very recent, very nice results, spectacular results on Zimmer conjecture by Hurtado, by Brown, Fisher and Hurtado, and also Federico Hertz. I mean, the rigidity of higher rank actions for big groups is a well advanced topic, and it always relies on hyperbolicity. Always. All statements on strong rigidity of C infinity rigidity of higher rank actions was always based on existence of hyperbolic or partially hyperbolic phenomena. Recently, the work on parabolic actions was conducted, and we are in this vein. We will work on parabolic actions. And why do we end up working with parabolic actions? Because we take any pair of matrices that commute and we try to perturb it. If AB is higher rank, well, it is rigid. If AB is not higher rank, it means there exists a subtorus, some torus TD1 inside TD, on which the action AB has a rank 1 factor. Rank 1 factor means that some iterate AKBL is identity on this torus TD1. So not higher rank means rank 1 factor. So, for example, you imagine your action is like identity B. If B is hyperbolic, or partially hyperbolic, you cannot perturb this into an affine action. If you perturb it, you take A equals identity plus alpha, and B equals B plus beta. And if you write that they commute, this will imply that alpha is equal to 0, because you will have that B, because you will have, so you have something, let's call this set T AB. It's equal to alpha beta such that A plus alpha, so alpha beta are vectors in RD, A plus alpha, B plus beta equals B plus beta, A plus alpha. And you see that in this case, TAB has the first coordinate 0 always, because this is the same as saying that A minus identity beta is equal to B minus identity alpha. This is the same set. Okay, and in the case B is hyperbolic or partially hyperbolic, there is no solution. Okay, A here is identity, so this is 0, and you don't have B alpha equals alpha, because there is no eigenvalue 1 for partially hyperbolic matrix. So the only possibility that you remain with, so this case will correspond to a case where there is no rigidity. We're happy with knowing this. I mean, we want to classify. We want to know what can you say for a pair of matrices when you perturb it. This pair of matrices, we know you cannot perturb. If you perturb, there will always be identity as a factor for the affine action, and so the affine action is never rigid. Cannot say that it is KM rigid, because you cannot add a translation here. Okay, am I clear? Any question? No. Okay. Now you say, what if the factor was identity? Then you get, for example, an action that is of the form A, because you want to look at the action on the full torus. So it's A times B bar, and now, or A tilde, or A prime. And now suppose A prime, B prime higher rank. And this we proved with Daniela in 5 or 6 years ago. We proved, or more even, that this action rho is KM rigid. And for this, we mix KM rigidity in the identity factor of the action. So you see, this is like you take R alpha cross A prime and R beta cross B prime. And you wonder, is this pair, is this affine action KM rigid? And Km rigid, remember what it means. You perturb A and B in a volume preserving way. You assume that the integral of the perturbation vanishes, and then is it conjugated to AB? And the answer is yes, if alpha, beta satisfy the simultaneous Diophantine condition. Anyway, for almost every alpha, beta, this pair will be Km rigid. Okay, but the story does not end here, because you have the most challenging case that is left behind, and this is the case. So the most challenging case is when A and B are parabolic. And this is the case that I will discuss today, and I will give a statement, and the statement is the following. So parabolic, what does it mean? So it's A minus identity to some power K to some power L to some power P must be equal to 0, and the smallest P is the step of A. Yes. And so if both are parabolic, we have the following theorem. So remember what is TAB. It's alpha and beta such that A minus identity beta equals B minus identity alpha. And we have the following theorem with Daniela and Masha. Whatever. Okay. What do we do? What do we do? We say the following, that there is a dichotomy if A, B parabolic. So these are parabolic matrices in SL and Z. If A is step 2, then we have the following dichotomy. One is that for any alpha, beta in TAB, the action, the affine action AB has a rank 1 factor that is not a translation, and so action not Km rigid. Okay, so really the answer here is that exactly like in this, I will show you example. You can perturb the action in this example, sorry. In this example, x plus alpha, x plus y, I showed you, you can perturb so that you preserve all rotation data, yes, but you are not conjugated to the linear model, to the affine model. 2, for almost every alpha, beta in TAB, okay, AB is Km rigid. Any question about the statement?
What does it mean, rank 1 factor?
Okay, rank 1 factor means there exists, so rank 1 factor. There exists K and L and D1 such that AKBL equals identity on TD1. There exists a projection on some coordinates. You will see a Z action, not a Z2 action. Clear? Example. Take A equals identity plus E21 plus E32. This is a step 3 matrix. Take B to be this, sorry, because we said A will be step 1. And A equals 1 plus E, say, 4, 5. Yes? These are parabolic matrices that commute. What is E21? It's just that this is like E21 is you look at line 2 and column 1. Okay, so this is yeah, this is your matrix B. Okay, now AB commute, and now if you look at T of AB, you will see that alpha 1, you will see that beta 1, no, you will see that alpha 1 equals alpha 2 equals 0. You see, because this times alpha must be equal to this times beta. This times alpha gives you the vector 0, alpha 1, alpha 2. The other guy will give you some beta 5 here, but these are then 0. Okay, if they are 0, it means that the action AB, whatever you take for alpha and beta, will look like this. So AB will look like this. A will look like A of X will be like X1, X2, blah, blah. And B of X will be X1 plus beta 1, X2 plus X1, blah, blah. So now if you look at the torus T2, the first coordinates, so X1 plus beta 1, X2 plus X1 is a rank 1 factor. Right? So this pair AB, the affine pair, has a rank 1 factor. And this factor is parabolic and not identity, not a translation. So as I showed you before, this can be perturbed, preserving volume and preserving rotation data and not linearizable, even though everything is Diophantine. So the action is not, I can give you another example, even simpler. Look.
Bassam, how much time do you need to finish?
I have 2 minutes. Can I have 5 minutes?
5 minutes is okay, but it is already 48 minutes to 2. Okay, 5 minutes.
Okay.
Yes.
Yeah. So you see, I give you another example where I take, for example, 1 plus E21 and 1 plus E31. So this is like X. These are step 2 matrices. So you get X, Y plus X, Z, and X, Y, Z plus Y. And now because of the commutation relation, you see that this guy, X here, alpha 1 equals beta 1 equals 0. So identity is a factor. Identity itself is a factor of the affine action. So the affine action itself can never be Diophantine because it has identity as a factor, not a translation. So this is never rigid. But for example, if I give you example 3, I take 1 plus, I take x plus alpha y plus x and x y plus beta, then for almost every alpha beta, you get rigidity. Yes, and if you take, finally, one more example, more complicated, you take 1 plus e2 plus e3 So this is a step 3 guy, and you take 1 plus e3 4. Step 2, and this is also going to be for almost every alpha beta in T of AB. So it has to commute. AB is Km rigid. Okay, so I say 2 words about the proof in these last 2 minutes. The proof is based on a Km scheme. The novelty is the fact that the cohomological equation that appear are equations above parabolic elements, and these parabolic elements are A and B. So you have HA minus H equals delta F, HB minus H equals delta G, and the commutation relation gives you delta F B minus delta F equals delta G A minus delta G plus phi. And now smallness is that delta F, when I write delta F like this, I mean delta F and delta G are less than epsilon, and phi is less than epsilon squared. And you want to solve this equation. And then you bump into the obstructions, and there are infinitely many of them, and you bump into the fact that L2 here is not tame. Remember what I showed you before, because B is maybe step 3, 4, 5, so this is not tame. What you do, you use the higher rank trick to deal with the obstructions and observe that they are not big, and you build a Km scheme in the sense that you can, of course, this is not exactly the linearized equation for the conjugacy. I'm oversimplifying it and cheating, but this is essentially the kind of equation you need to solve. So you solve this plus an error, and usually in Km scheme, to have a converging Newton scheme, you want the error to be quadratic in epsilon. And you are kind of in good position because phi, which calls for the obstruction, is quadratic. However, the equation is not tame. So, and here is the last word, you can solve this. So solve star, but such that delta F tilde, which means both delta F tilde and delta G tilde, is quadratic, but not in CR norm. It's less than phi in CR plus tau. And C here is some constant that is related to step. So C is essentially step B, which means you do have and delta H is of order delta F. And here there is no loss of derivative. So you have a Km scheme in which you conjugate, and at each step, the error after conjugating is quadratic, but up to loss of derivatives that is maybe very big. Nevertheless, this loss of derivatives is not at all a problem in the Km scheme. Okay, you would have a problem when people say, if I lose half of the derivatives, I cannot apply KM scheme. This is when you lose the derivatives here. So for example, if delta HR is equal to this with a loss here mu that is less than 2, you're fine. But if mu is bigger than 2, you're not fine. However, if C here is 10 or 20, you're okay. You can work. And how do you solve this? With the lemma that says that for AB parabolic with a step 2 and under alternative 2, so you do use the alternative 2 that there is no rank 1 that is not a translation, you have that A, K, B, L of any vector M will grow bigger than C to some power M over 1 over a step B. And here it's for any K in Z, for any L positive or L negative. And here, sorry, I didn't say, but M is such that AK of M is bigger than M for all K in Z. That's it. This is more like for the experts. It's everybody knows that to solve the higher rank, this is the dual action of A and B. That to kill the obstructions, you need to compute some sums of the dual orbit on the Fourier coefficients. And to do this, you need to control a growth on the dual orbits. When you have a partially hyperbolic action, you control the growth on the dual orbit. When you have parabolic action, it's harder to control the growth. There are no directions of stable and unstable direction. And you manage to control, but with the loss, and an important loss here that is like you control the growth, but like square root of M or M to the power 1/3. And this causes the loss here, but it doesn't matter. You still can do your KM scheme. We don't know for higher step actions A and B, when they are both higher step, we don't know if rigidity holds or fails for the moment. And I finish. Thank you.
Thank you very much. We have a very short time for questions. Are there any questions or comments? Well, thank you, Bassam, for your very interesting talk. Let's thank the speaker. And we resume in 1 hour and 2 minutes. So see you at 4 p.m. Moscow.
Thank you. Bye.
Thank you.
Bye.
Bye.
Алексей, вы меня слышите? Клименко.
Да, слышу.
Слушай, а как я узнаю, когда я ЧМН? Это где пишется?
Мы напишем, мы сейчас распределяем как раз
ЧМН. Понял, да. А я так смотрю, вроде нет, думаю, может, я что где пропустил, какую информацию. Окей, спасибо.
Леш, меня только в среду не ставь, ладно?
Да, я видел все письма, просто не успел ответить.
Хорошо, ладно. Ага, всем счастливенько, спасибо большое. Ладно. Можно выходить, да, до 4, правильно поняла?
Ну да.
Ладно, хорошо.
А что до 4 сейчас не будет, что чего-то?
Обед.
У нас обед есть, смотри-ка ты. Вот это здорово. Алеша, а вы общались с Яшей Песиным или нет по поводу конференции?
Общались, но как-то, не я общался, вернее, но, по-моему, как-то не было ответа.
То есть вы не знаете, как там дела у него, чего, да? Ладно, я вам сам напишу, конечно. Ага, вот, я вас вижу, оказывается. Я что-то слышу. Понятно, ладно, узнаю. Там есть еще Миша.
Алексей?
Да, да.
Здравствуйте, это Мира. Я следующий докладчик. Я подсоединилась сейчас своим iPad'ом тоже, так что у меня будет 2.
Угу.
Скажите мне, пожалуйста, во сколько мне надо быть здесь, чтобы вам было
без
удобно?
10, я думаю, за 10 минут мы справимся.
То есть я уже вся подсоединена. Единственное, что надо будет сделать, это сделать share screen.
Ну, давайте попробуем. Можем сейчас, конечно, попробовать сейчас.
Нет, ну, я думаю, что я не думаю, что этот доклад будет сильно отличаться от других, в том смысле, что технология это та же самая. Ну, сделайте меня ко-хостом, и я сделаю шерсткой.
Ну, да.
Но вы хотите в без 10. И у меня 45 минут, включая вопросы.
Ну, плюс-минус там. Если вопросы немножко вылезут, ничего страшного. То есть можете считать, что у вас 45 плюс вопросы. Ну вот, в общем, то есть перерывы у нас щедрые, поэтому есть возможность.
Но лучше держаться, значит, 45 максимум.
Да.
То есть 40 минут плюс 5 минут вопросы, и после этого 15
минут. Например, да.
Да, я понял. Все, спасибо большое. Тогда я буду здесь без 10. Спасибо.
Мира, а вы откуда? Говорите так хорошо по-русски?
Ну, я вообще-то до 16 лет жила в Советском Союзе.
О, это все-таки давно было немножко, так здорово.
Да, тогда еще был Советский Союз.
Да.
Государство, из которого я уехала, больше не существует. Да, это правда.
А где вы сейчас?
Сейчас я в Лондоне, но вообще-то я израильтянка. Я в 16 лет переехала в Израиль, а потом...
Это какой год был?
92-й.
Вот, у меня брат в это же время уехал там туда.
Ну, мы должны были уехать, наверное, даже раньше, но нас не выпустили. Мы были, по-моему, последние...
Откуда вы уезжали?
Мы уезжали из Баку, и нас не выпускали, потому что...
То есть вы азербайджанка, понятно.
Господи, Бог с вами, я еврейка, я ашкеназская.
Вы же из Баку.
Нет, мы жили в Баку. Если вы из Советского Союза, то вы знаете, что люди жили совсем не там, где они родились или где жили, а там, где им давали... А там, где им давали хорошие квартиры. Нет, а там, где им давали хорошие квартиры. Вот, и в Баку папе дали прекрасную квартиру, и поэтому бросили все остальное и переехали туда.
Моя мама тоже жила до войны в Баку. Она говорила, Баку – это маленький Париж. Такие слова.
Баку был хороший.
Вы давно в Баку были?
О, Господи, в 95-м.
95. А в каком городе в Израиле вы живете?
Я живу не в Израиле сейчас, я живу в Лондоне.
Вы уже переселились-таки в Лондон?
Ну,
да. То есть там, где живет наш Дима Тураев. Вы его знаете, Диму Тураева?
Не лично.
Специалист динамической системы.
Не лично. Я знаю имя, но я не знаю его лично.
Да. Он с Нижнего Новгорода, то есть вот откуда мы, вот откуда я. Я из Горького, бывшего. Вы помните, такой город был в Советском Союзе, Горький?
У меня дедушка был на военном аэродроме в Горьком, начиная с 43-го года.
Вы, наверное,
до конца
знаете
войны.
песню Макроусова «Над городом Горьким, где ясные зорьки». Не помните такую песню?
Нет, такой нет.
Странно. Я думаю, что если бы я вам сейчас сыграл, вы бы спели эту песню, потому что ее все знают. Над городом Горьким, где ясные зорьки. Это такая песня такая про Сормова. Вот. Так что чуть-чуть вот это такая совершенно советская песня, ее знают все.
Я знаю много советских песен, но именно эту песню я не знаю.
Ну вы должны были знать, 92-й год, еще дети пели того возраста, дети пели эту песню. Я думаю, что вы не могли ее не знать.
В 92-м году дети моего возраста пели исключительно репертуар группы «Кино».
Ну да, это да, было такое.
И мы все выходили на улицы после 15 августа
Уже
90-го года и кричали «Цой жив».
Алеша, это ничего, что мы тут говорим по-русски?
Ну, вас транслируют на весь мир в Ютубе. Покажется, записи не останется.
Но мы ничего плохого не говорим.
Вроде да. Мира, мы вас сделали ко-хостом. Правда, я не знаю, правильный или неправильный аккаунт. Там же
Нет, аккаунта, вот тогда давайте проверим действительно, что я могу сделать. Я думаю, аккаунт тот же самый, это же просто с разных...
Ну, в смысле, да.
Нет, вы меня сделали не там. Нет, могу сделать шер-скрин.
Дима, поменяйте, пожалуйста. Раз
да,
он...
сейчас.
Да, он говорит, что он ледогостки.
Сейчас делаем.
Ага, все, вот теперь он говорит, что я ко-гост, и вот теперь давайте-ка попробуем. Раз, два, три. Чудесненько, просто дивно. Я тоже буду писать, если вы не возражаете, потому что как-то, конечно, технология продвинулась. Я все-таки предпочитаю максимально приближенное к доске.
Ну, хорошо.
Сейчас, одну секунду, мне нужно, тут у нас господин пришел газ проверять, мне нужно его проводить, и я вернусь. Сейчас, секунду.
Ну, хорошо, да. Ладно, ну, вроде все работает.
Алексей, вы здесь?
Да.
Я хотела задать один вопрос. Это немножко, конечно, поздно. Надо было спросить, но эта конференция, она, в общем, в целом про динамические системы, и операторы Шрёдингера немного выбиваются, хотя я видела, что будет достаточно много докладов как раз именно про почти матьё. Но вопрос в том, что я имею право, скажем так, предположить о базовых...
Я думаю, что поскольку ваш доклад первый, вам придется просветить аудиторию про это.
А то есть я буду первого проходит.
То есть кто-то там про это что-то слышал, но, наверное, как сказать, вот...
Тогда вопрос больше к вам, как к организатору с точки зрения вкуса. Что вы предпочитаете, чтобы я рассказала про меньшее количество результатов, но зато затронула технические подробности, или рассказать все результаты? Ну, у нас 3 результата.
Я думаю, что это лучше, вот, так сказать, обзорно, без
технических подробностей, не входить в доказательства.
Ну, видимо, да.
Да, хорошо, тогда как раз и будет 40 минут. Ну, тогда медленно начну. Хорошо, договорились. Спасибо большое. Спасибо.
Et puis elle a appelé France Inter, rubrique réagir.
Сахарку мне подсыпала?
Нет. Что ж это дело индивидуальное?
Хорошо. Так.
Нормальное варенье, по-моему.
Очень хорошее варенье, кто говорит, что. Кто-то там говорил, что оно плесневеет, это неправда. Ложечку дашь? Ого!
У вас звук включен.
Сейчас, постойте, а у меня тоже включен.
Да. Ага.
Так, все, всех приветствую. Видимо, я ее оставил у себя там. Скоро начинаем. Сейчас, секундочку. Смотрю на время. Да, 1 минута осталась. Спасибо. Мира, вы здесь?
Да. Я только не вижу
Миру
себя
мы
на
видим,
экране.
Миру видим.
Да, все. Отлично. Ждем последнюю минуту.
Угу. Как скажете. Я только слушаю и подчиняюсь.
Мира, вы в Лондоне где?
Queen Mary.
Queen
Queen Mary.
Ага. So next we resume. Next speaker of our evening session is Mira Shamis from Queen Mary, London. Mira, please.
Thank you very much. So first of all, I would like to thank the organizers for inviting me to this conference. It's a big honor for me to talk here. My talk is a bit different from the previous talks in the sense that it's not precisely about dynamical systems, although there is a dynamical system on the background. So this work is based on a joint work with Arthur Avila, Yoram Last, and Kiju. And this is a very fresh work. It's just now appeared on the archive. In this work, we study one-dimensional discrete Schrödinger operator, which is called the almost Mathieu operator, which is defined as follows. It is the operator that acts on L2 of Z by H alpha lambda theta psi of n equals to psi n plus 1 plus psi n minus 1 plus 2 lambda cosine 2 pi alpha n plus theta psi n, where lambda is some real number, which is the parameter that is called coupling constant. And you can think of it, so this part is the free discrete Laplacian. So you can think of lambda as a strength of the disorder. And we also can assume that lambda is actually positive because the change of the sign of lambda is simply translation of theta by pi. Alpha is some number between 0 and 1. And theta is between 0 and 2 pi. Now, one can easily see, so I have seen in the program that there will be actually several talks about almost Mathieu operators, so I'm the first one. So maybe I will give you quite an, as much as I can, extensive introduction. So one can see that if alpha is a rational number, P over Q, then the operator is periodic of period Q. And if alpha is irrational number, then the operator, what it's called, almost periodic. Sometimes it is also called quasi-periodic, and in some other literature, it is called one frequency operator. So there are several names. Oh, and before I forgot, please stop me at any time if you have any question. Now, it is known that the spectral properties of the almost Mathieu operator depends very sensitively on the arithmetic properties of alpha, which is called the frequency. So for example, back in 76, Gordon proved that any Schrodinger operator, which is very well approximated by periodic operators, can only have continuous spectrum, only. Using this result 6 years later, in 82, Avron and Simon proved that in the regime, the so-called supercritical regime, when lambda is greater than 1, the spectrum of the almost matter operator with very well approximated frequencies is purely singular continuous. On the other hand, in 99, in the same regime, lambda greater than 1, Zhytomyrsky proved that the spectrum of the almost matter operator for poorly approximated frequencies, Diophantine frequencies, is pure point for almost every theta with exponentially decaying eigenfunctions. And now I'm talking about well-approximated frequencies, poorly approximated frequencies, and now it's a time to explain what exactly I mean. So in 94, Zhytomyrsky introduced the following arithmetic parameter, beta of alpha, which is
a question.
Yes, yes.
You mean that alpha is not rational, then it is almost periodic. So
yes,
periodic.
When alpha is rational, then the operator is periodic. And we know a lot about periodic operators using the standard Bell-Floquet theory. So we will concentrate on the case that alpha is irrational, in which case the operator is almost periodic.
Okay, thank you.
So beta of alpha is equal to the lim sup when q tends to infinity minus 1 over q, logarithm of the minimum over p of the distance of alpha from p over q. And this can be rewritten as lim sup when n tends to infinity of logarithm of qn plus 1 divided by qn, where pn over qn is the sequence of convergence of alpha. Namely, the sequence that arises from the continued fraction expansion. So you can think of this beta alpha as an indicator of how well alpha is approximated by rationals. So in case that this parameter beta of alpha is strictly positive, then we will say that alpha is very well approximated by rationals. And those are the so-called Liouville numbers. And in case that beta of alpha is equal to 0, those are poorly approximated frequencies, and they conventionally called Diophantine numbers. Now, Zhytomyrsky made the following conjecture. So this whole thing, this difference between the singular continuous spectrum for the well-approximated frequencies and pure point spectrum for Diophantine frequencies gave an indication that there may be a phase transition. So Zhytomyrsky made a conjecture that the spectrum is purely singular continuous if lambda is between 1 and e to the beta of alpha, and it is pure point if lambda is strictly greater than e to the beta alpha. This conjecture was recently proven by Avila, Yu, and Zhu in 2017, and independently by Zhytomyrsky and Liu in 2018. Now, the purpose of our work is to show that some of the spectral properties of the almost matter operator with very, very well approximated frequencies, namely when beta of alpha is positive, are very miserable. And in fact, they as bad as at all possible in the class of all one-dimensional discrete Schrödinger operators. Also, one of the things that I should mention is that we work not only in the so-called supercritical case, lambda greater than 1, but also in the subcritical case, when lambda is smaller than 1, in which it is known today that the spectrum is purely absolutely continuous, namely the nicest one, and still very strange, very abominable things happen there. So we focus on the following characteristics of the spectrum. So first, the Hausdorff measure of the spectrum. Second is the regularity of the integrated density of states and of the Lyapunov exponent. And third, properties of a spectrum as a set, homogeneity, and the Parov-Vidon property of the spectrum. And I will start with the Hausdorff measure of the spectrum. And in this part of the talk, we'll concentrate only on the critical case. So this is my first point. We'll concentrate on the critical case, so-called critical case, when lambda is equal to 1. Now, in this case, it is well known today. I'm going to write down a very simple and elegant looking statement. And actually, it took more than 35 years to prove that statement. We know that the spectrum is a Cantor set of zero Lebesgue measure. And therefore, the question about its fractal properties naturally arises. Back in 2016, together with Lust, we proved that there exists a G delta dense set of frequencies for which the Hausdorff dimension of the spectrum of the critical almost Mathieu operator is equal to 0. Now, this statement can be reformulated in terms of Hausdorff measure as follows. First, let me remind you the definition of the Hausdorff measure. So we will define T for a given set K. We will define T Hausdorff measure of a set as follows. We will cover the set by intervals of lengths at most epsilon, and then we will add the T's powers of the lengths. And then it is not hard to prove that the Hausdorff dimension of the set is equal to 0 if and only if T Hausdorff measure of the set is 0 for any positive T. Now, there are other examples of operators with zero Hausdorff dimensional spectrum, and you consult the survey paper by Damanik and Filman for these examples. Now, the natural question that we ask is the following. Can we replace in this definition the piece power with a more refined scale of a gauge function? So for that, first, let us modify this definition a bit. And for a given function omega, we will define omega Hausdorff measure, which will be precisely the same thing, except that instead of applying piece power to the lengths of these intervals, we will apply the function omega to the lengths. So let us define omega Hausdorff measure. And everything else stays the same. And then it turns out that the right scale to talk about in this case is the function omega t of s, which is 1 over logarithm to the power t of 1 over s for any positive t. Now, it is known that for any discrete, one-dimensional, discrete Schrödinger operator of the form minus Laplacian plus potential, omega 1 Hausdorff measure of its spectrum is always strictly positive. And we will talk about this particular point a little bit more in a couple of minutes. Now, in our first result, we showed that this cannot actually be improved, even for the almost Mathieu operator. So our first theorem is the following. So let S alpha 1 be the spectrum of the critical Mathieu operator, critical almost Mathieu operator. Then 1, if alpha is Liouvillean number, namely it's a very well approximated by rationals, then for any t greater than 2, omega t Hausdorff measure of the spectrum of the critical almost Mathieu operator is equal to 0. Now, this part applies for t greater than 2, and it seems that there is still gap between that result and between what we said, the optimal result. And in the second part of our theorem, we showed that we can actually go up to omega 1. So second, if omega is any non-decreasing function with omega of 0 equal to 0, this such function is sometimes called in the literature gauge function, which decays faster than omega 1. Then there exists a G delta dense set, bare generic set of frequencies such that the omega Hausdorff measure of the spectrum of the critical almost multi operator is equal to 0. Now, this theorem concerns the critical case. And one can claim that all kinds of very strange things can happen once we're dealing with the critical case, not only for the almost multi-operator, but actually in any critical case. Our next results show that actually very strange, abominable things can happen once we are dealing with Liouville, very well approximated Liouville frequencies. So my second subject that I would like to discuss is the regularity of the integrated density of states. Now, recall that the theta averaged integrated density of states is given by, we're going to denote it by curly n with subscript alpha and lambda. And this is the limit when n tends to infinity, 1 over n. The average over theta, simply the integral from 0 to pi, of the number of the eigenvalues of the restriction of our operator to the interval 0 to n minus 1 in Z that are smaller than E. Okay, and when alpha is irrational, this average can be replaced with the pointwise limit. Now, we would like to know how continuous, how regular the density of states is. For that, let us define a class of functions. So for a modulus of continuity omega, we define a class of uniformly continuous complex valued functions with a modulus of continuity majorated by this function omega. Okay. Now, a classical result in potential theory called Frossman's lemma shows that if a set has a small Hausdorff measure, then it cannot support any regular measure. Namely, if the spectrum is small, then the integrated density of states is irregular. However, the opposite direction is not true. To be a little bit more precise, Frossman's lemma says the following, that the omega Hausdorff measure of a set is positive if and only if there exists a measure which is supported on that set, which is regular with the same, exactly the same modulus of continuity, omega.
Please repeat, what does it mean that the set is regular?
It's not regular. We're saying that there is a connection between the Hausdorff measure content of a set and between the regularity of the measures that can be supported on that set. And the statement is that the Hausdorff measure of a set is positive if and only if there exists a measure which is supported on that set, which is regular precisely with the same modulus of continuity, omega.
Mm-hmm. Mm.
Okay, so and
so could I ask you, what do you mean?
Yes.
What do you mean that the measure is regular with this modulus of continuity?
You have this omega Hausdorff measure, and then you ask yourself how regular the measure is. So in the sense of Hölder continuity, is it log Hölder? Is it exponentially Hölder? And then the models of
what does it mean? What does it mean to say that the measure is
log Hölder?
Yes, for example.
Then it means that f of a minus f of b is smaller than or equal than a minus b root.
So the distribution function of the measure, it's a measure on the interval, and the distribution function is h.
Yes, precisely.
Yes. Thank you very much.
So the corollary from this Forstmann's lemma is the following, that if omega Hausdorff measure of the spectrum is 0, then the corresponding integrated density of states is not uniformly omega Hölder continuous. And for example, from our work with Lust, the integrated density of states is not uniformly Hölder continuous for any positive exponent. So in this case, omega s is equal to s to the t. Okay. Now, by result of Craig and Simon from 83, for any ergodic Schrödinger operator, the integrated density of states is always uniformly log Hölder continuous. And later, Bourgain and Klein extended this result to the non-ergodic setting. So, and here we can go back to this claim that here, that I stated here. So from here, we see that since for any Schrödinger operator, the integrated density of states is always a log Hölder continuous, then we see that indeed omega 1 Hausdorff measure of the spectrum is always strictly positive. Simply as a corollary from Forstmann's lemma. Now, this result is optimal in the sense that Craig in 83 and Gunn and Kruger in 2011 constructed examples of, this is Kruger, constructed examples of Schrödinger operators with almost periodic potentials for which these cannot be improved. Okay. Now, our first theorem combined with Forstmann's lemma immediately imply that log Hölder continuity is optimal in the critical case. Okay. Outside the critical case, when lambda is not equal to 1, such simple considerations do not work anymore since the spectrum is of positive measure. So what do we know in the general case of arbitrary positive lambda? Not that much. So we know, first of all, the following. In 2010, Avila and Zhytomyrskaya pointed out that for bare generic G delta dense set of frequencies, the integrated density of states is not uniformly Hölder continuous for any positive exponent. Now, there is a completely 180 degrees opposite picture for the poorly approximated frequencies, for Diophantine alphas, in which in 2008, Avila, following the works of Goldstein, Schlag, Avila, Zhytomyr, Scan-Bourgain, proved that if our parameter beta is 0, namely alpha is poorly approximated by rationals, then the corresponding integrated density of states is always uniformly half-Hölder continuous outside the critical case. Now, in our next result, we show that if we are dealing with Liouville frequencies, with very well approximated frequencies, then actually log-Hölder continuity, not a T-Hölder, but log-Hölder continuity is optimal for arbitrary positive lambda. So our theorem, second theorem states the following. So first, if our lambda is between e to the 2 beta alpha over 3 and e to the minus 2 beta alpha over 3, then the corresponding integrated density of states is not uniformly omega t Hölder continuous for any t greater than 3. Our second item now, if we will restrict our assumption on lambda a bit, namely now we will take lambda between e to the beta minus beta of alpha over 2 and beta of alpha over 2, then the corresponding integrated density of states is not uniformly omega t Hölder continuous for any t greater than 2. And once again, there is a still gap. And in our source point, similarly to the first theorem, we can show that we can actually go up to the omega 1 in very similarly to what we did in the first theorem. If omega is a gauge function, decaying faster than omega 1, then there exists, then let us put it this way, then for any lambda which is not 0, there exists a bare generic set of alphas for which the corresponding integrated density of states is not uniformly omega Hölder continuous. So in insert point, we can actually go up to the omega 1. Now, to the best of our knowledge, all 3 points are the first explicit examples of almost periodic potentials, of almost periodic Schrödinger operators with such low regularity of the density of states. And an interesting feature of our construction is that in the subcritical case, when lambda is strictly smaller than 1, as follows. So first of all, the spectrum, as I already mentioned, purely absolutely continuous, and also as follows from the work of Avila and Damanik, the integrated density of states is also absolutely continuous. Now, all these properties imply similar properties of the Lyapunov exponent. Now, the Lyapunov exponent is connected, I will say very briefly, so if you don't know what I'm talking about, you can ignore me completely. The Lyapunov exponent is connected to the integrated density of states by a very famous formula called the Thouless formula, which goes back to the work of Thouless, Herbert, and Jones. Now, there is an argument of Goldstein and Schlag that provides the connection between the regularity of the integrated density of states and of that of the Lyapunov exponent. Their argument, however, which is written in their paper, does not formally cover our omega t. So therefore, we needed to generalize this argument a bit to cover our omega t. And from this generalized proposition, we have the following corollary, that for any t greater than 2, if the integrated density of states is not, it's a general proposition, not about almost matter operator, is not uniformly omega t Hilbert continuous, then the corresponding Lyapunov exponent is not uniformly omega t plus 1 Hilbert continuous. So therefore, all these results are valid also for the Lyapunov exponent if you simply increase t by 1. Now, our last result is motivated by the inverse spectral problem for quasi-periodic operators. And I will not go into too many details here. However, let me first describe you what the problem is. So the question that one wants to ask is the following. Given a compact subset of the real line, we would like to know what are the spectral properties of Jacobi operators whose spectrum coincides with that particular compact set. In 95 and 97, Sodin and Yuditsky studied this problem in the class of Jacobi operators with almost periodic potentials. And they proved that if the spectrum is homogeneous and the diagonal elements of the corresponding resolvent operator are purely imaginary on the spectrum, then the operator is almost periodic. Now, to the best of our knowledge, these works, and also all the following works, all of them, that dealt with the inverse spectral problem, either required homogeneity of the spectrum, which means that it cannot be too meager near any point, or a much weaker condition, which is called the Paravidon property, which in essence tells us that the space of analytic functions on the complement of that set is sufficiently rich. Now, then the natural question arises, does the homogeneity, or at least this weaker Paravidon property, hold for simple quasi-periodic operators, such as the almost matter operator? And surprisingly, the answer is actually not always positive. First, let me remind you the definition of a homogeneous in sense of Carlson set before I'm formulating our results. So we say that a set K is homogeneous if there exists epsilon naught and tau between 0 and 1, such that for any point in the set and any epsilon smaller than epsilon naught, the measure of the intersection of that set with the interval centered at that point of length to epsilon is greater than or equal than tau times epsilon. Namely, it cannot be too meager near any point. I will not give you the precise definition of the Parvidum property. Now, up until now, all the results that we are aware of dealt with Diophantine frequencies. So, for example, the result of the Mani, Goldstein, Schlag, and Voda from 2018, the result of Legal, Yu, Zhao, and Zhu from 2017, they all dealt with poorly approximated alphas. And they show that in this case, the spectrum is homogeneous, and in particular, satisfies the Parvidum property, since it's the much weaker property. Recently, Simon conjectured that the spectrum of the almost Mathieu operator is homogeneous outside of the critical case, outside the case that lambda is equal to 1. And we disprove this conjecture in quite a strong sense, and we prove the following result, our third and last theorem, that if lambda is between e to the 2 beta of alpha over 3 and e to the minus 2 beta of alpha over 3, then the spectrum of the almost Mathieu operator is not homogeneous. And second, if now we will restrict our assumption on lambda a bit, lambda is between beta alpha over 3 and e to the minus beta of alpha over 3, then the spectrum of the almost Mathieu operator does not satisfy the Parvidum property. And to the best of our knowledge, these are the first examples of ergodic Schrödinger operators with a spectrum of a positive measure, which is not homogeneous and does not even satisfy the Parvidum property. And in particular, these examples imply that the solution to the inverse spectral problem, which would include the almost Mathieu operator with well-approximated frequencies, may require essentially new methods, because none of the usual assumptions, the strongest of which is homogeneity and the weaker of which Parvidum property, are not satisfied. And I would like to stop here. Thank you very much.
Thank you. Are there any questions or comments?
Could you explain the last statement you made on the inverse spectral problem?
Yes, all the works which I'm aware of and all the techniques that I'm aware of that deal with the inverse spectral problem require a property on a set. So the homogeneity, the Parvidum property, and there is third property in between, which is called direct Cauchy theorem property. They're all properties of a set, has nothing to do with operators. But if those properties are not satisfied, none of the methods with which today is possible to solve the inverse spectral problem do not work. Which means they cannot be applied in this case. So, which means that if one would like to solve the inverse spectral problem for the almost Mathieu operator with Liouville frequencies, he needs essentially, conceptually, other new methods.
Thank you.
What does it mean, Parvidum property?
It means, in the essence, that the space of analytic functions on the complement of the set is sufficiently rich. So this is the image that I would like you to hold in mind.
I see. Thank you. Any other questions? Well, let us thank the speaker.
Thank you very much.
We have a 17 minutes break until 5 p.m. Moscow time.
Thank you very much.
Thank you.
Что-то хотел тебя, можно тебя спросить, да?
Сейчас, минуточку.
Это еще не выключится.
Hi, Christian.
Hello, Olga.
Hello. How are you?
Fine, fine.
Fine.
As well as possible.
Hello, Christian.
Hello, Yuli.
How is your granddaughter?
Ah.
Good evening, dear Christian.
Hello, hello, Slava.
I'm glad to see you.
Yes.
Where are you from at this moment?
I'm at the university in Dijon.
Ah, it's native. Indeed. How are your little children?
Nice.
Nice? Okay.
Yes.
Beautiful.
She's growing almost 1 year now.
Okay.
11 months.
Mm-hmm. Beautiful.
She can go, Christian.
Sorry?
She can go.
If she can walk, not yet.
No, not yet.
She can walk with using the four, using the hands on the legs. Yes. And she start to stand, but.
Christian, Tanya.
Hello.
Татьяна Борисовна.
Таня, привет.
Как здорово.
So you are
Beautiful
home.
life. It's possible to see very many people simultaneously. Оля, починками.
Татьяна Борисовна, здрасте.
It's not far from.
And where are you, Olga? There is a
I'm at
painting.
home. I'm
Sorry?
at home. At home. At home.
At home. Okay.
In Nizhny Novgorod.
Я через 25 минут должна уже выскочить. Гасить свет.
Да нет, оставь. Окей.
Okay.
Оля, а последний раз Christian еще не было пандемии, да? It's not.
Last time Christian visited us in 19th year in December, if you remember. Yes, before pandemic.
Before pandemic. It was beautiful fact.
Time.
It's possible to visit.
Yes, and now pandemic is hard in Russia, it seems. But
yeah, in France, situation is better.
For the moment, yes, but
it's okay.
It's increasing again. So let's see.
But it's possible to travel, Christian, from France to some place.
Sorry?
It's possible to travel now for you.
Yes.
Yes, it's possible. Yes.
Yes.
But you must be healthy.
Yes. With vaccine, yes.
Not so easy. At this moment, I don't know our certificate is good for France or not.
I don't know. I don't know. I think we can check that on internet, but I don't know. In fact, my computer died yesterday night, so I had some difficulties for preparing my talk.
Computer died.
Yes, completely.
Конференция, good evening.
Due to coronavirus?
No, not due. I guess not.
Конференция.
Lorenzo, you are from Brazil at this moment?
Well, yes, I am at this moment from Brazil. I follow your discussion.
Okay.
I think that, for instance, with the coronavirus vaccine, that is the most popular or most frequent in Brazil, it's not possible to travel to Europe. And indeed, I heard some colleagues that complained that the AstraZeneca, I was very lucky because I got 2 shots of AstraZeneca. I think that when you have your certificate, there is AstraZeneca producing in Oxford and the AstraZeneca produced in Brazil, because Brazil is producing also AstraZeneca. And in some places, they are complaining about the AstraZeneca produced in Brazil. And then I think that traveling is not that simple. You know, I was thinking to travel in February, but I am quite skeptical about the situation in winter in Europe, but I don't know. But I don't know.
So tell me if you...
I will tell you, but...
Yes,
I told you about...
Tell me when you can.
No, I mentioned you this 2 weeks ago. I think maybe you forgot, but don't worry. But okay. Well, let
Hi,
me say
Lorenzo.
hello. Hi, Julie. How are you?
Very good. How are you, Lorenzo?
Well, I'm fine. I think that now the situation in Brazil is better than in most of the countries of Europe. Then maybe we can be proud of it. I don't know. I think that the vaccine is progressing and the number of deaths is decreasing. Well, I cannot tell you that the situation here is good, but it's, I think that, for instance, if you compare with Germany, the situation is much better here now.
Wonderful, wonderful. Is the majority of people vaccinated or not?
Well, I think that this depends. I think that in Brazil, all the vaccination start a little late. But I think that now, 45% of the people have the two doses of the complete, and 75 has at least one. And this is not that in Brazil, that is not that bad because the population here is relatively young. If you compare, for instance, with other France or Spain. And the numbers of vaccination is increasing, well, slowly, but I think that in Brazil it's a little ironic because the president is against vaccination, or but the people go to vaccinate because there is a huge tradition, and the system in Brazil is very good, it's no bureaucracy at all, very quick. I think that, well, let's see what happens,
That's good, that's good. And the vaccination is not expensive.
No, but the vaccination in Brazil is completely free. The only way that you can get the vaccine is in the public system.
I see. Wonderful.
In São Paulo state, there is a city called Serrana that is I think that it may be that has about 100,000 people or something like this. In the beginning of the year, the state government did a program for vaccinate all the population, a special program. And the result was that the number decreased very, very quickly. And now, 6 months later, apparently there are many people with coronavirus because the vaccine the effect is ended, but the number of deaths is very low. At least that means that the vaccination was very good to prevent serious illness. That this is the point of the vaccination. I don't know.
Good. Christian, is it your painting behind you?
Ah, yes, it's one of my paintings, yes.
Painted, yo. Как nice. Beautiful.
Yes.
Кастрюля, пап, не чайная ложка.
У меня включен микрофон.
Ну ничего, пусть знаю.
Хорошо. Хорошо.
Could we ask the real organizers to allow Christian Donati to share his files?
Sorry? I don't know at what time I can share.
Yeah, I think we could start in 3 minutes, but can someone allow Christian to share his files?
So let's see if I can share. Yes, I can share.
Oh, you can share. Oh, wonderful.
Okay, I can share.
Okay, perfect.
I hope. What is that? Okay, it's not closed.
Кристиан Бонати рассказывает. Кристиан Бонати рассказывает.
Yes, it's
Yes,
perfect.
that, I hope it's.
Yeah, it's perfect.
Okay, so I guess it's a good one. So you can see my file?
Yes.
And
Yes.
it's moving when I do that?
Yes.
Okay, so it's okay.
Через 2 минуты начнется.
Beautiful text. Color text.
So what time is it? It's almost time, I guess.
1 more minute.
1 more minute. Okay.
Okay, so hello everybody. We are about to start. If possible, I'd like to remind everyone to mute themselves so that we only hear the speaker. It's my pleasure to introduce Christian Bonatti from University of Bourgogne, who is going to talk about non-algebraic and also flows in higher dimensions. Please go ahead.
Thank you, Omri, for the introduction. Thank you for the organizer for this invitation. Indeed, I have also to thank my informatic engineer because my computer died this night and I'm only able to make this talk because of his help. I hope it will be okay. So my talk is about Anosov flows in dimension larger than 3. So let me recall what are Anosov flows. First, the name comes from the works of Anosov in the 60s, when Anosov was studying the geodesic flows of manifold with a negative curvature in the qualitative but also quantitative with a quantitative question also, but I'm most interested in the qualitative one. So he extracts a structure that he called U-system. At this moment, if I'm not wrong, Smail traveled in Russia and meet Anosov. And Smail had the ideas of first more Smail system, but also of the horse show on speaking together. So, okay, so it has been a rich exchange of ideas. But okay, the U system was able to with the U system, Anosov was able to prove the existence of stable and unstable manifold on foliations. He had what is so now called the Anosov closing lemma, which is closer to what is called also the shadowing lemma. That is, you can approach recurrent orbit by periodic orbit, not by perturbation of the system, but already existing periodic orbits. And also he proves the structural stability of the geodesic flow on manifold with negative curvature using the structure of U systems. So this notion of U system, we can see all the hyperbolic theory of Smail as a generalization of these U systems. And it has been very important for the study of the qualitative study of dynamical system, in particular because hyperbolicity is a characterization of structural stability. So structural stability is something a little bit paradoxal because we are looking chaotic dynamics. Chaotic dynamics means that if you make any small mistake of the initial data, then the orbit will diverge completely, and so we have nothing to say one with the other after a short time. But structural stability say Yes, but if you perturb the system by itself, it remains exactly the same qualitative behavior. More precisely, it will be conjugated or topologically equivalent to itself. And then this structural stability is indeed equivalent to hyperbolicity with some transversality condition. And that is a long story starting in the 60s with some important result in the 70s and ending with Magnier in 88 and Hayashi in 98. So these U systems are the system where the hyperbolic structure on the wall manifold, and they are called now Anosov systems. So they are Anosov diffeomorphisms and Anosov flows. Let me recall these definitions. So if you first, most of my manifolds, so sometimes there will be boundary, but usually when I did not say it, my manifolds are closed manifolds, that is compact without boundary. And so I'm looking at diffeomorphisms on a closed manifold, and we say that it is an Anosov diffeomorphism if the whole tangent bundle of the manifold split in the direct sum of two subbundles, which needs to be invariant. So that is, if you apply df, the derivative of your map, to one bundle, you keep the same bundle, but not at the same point. The same for the unstable one, okay? And the other thing is that if you iterate enough, but uniformly enough, that is, there exists an n for any point, there is n that, so that if you take any vector in the stable, in the ES direction, it will be contracted by a factor like 1/2, and any vector in the EU direction will be expanded by a factor at least 2. And then ES is called the stable bundle, and EU is the unstable bundle. We will say shortly that ES is uniformly contracted and EU is uniformly expanded. If you look at now flows on not, so vector field on not diffeomorphism, then there is one direction which is never contracted nor expanded. It is the direction of the vector field itself. So the structure has to be adapted. And so what we required is that the tangent manifold of the tangent bundle of the whole manifold is the direct sum of 3 bundles, the stable one, the direction of the flows, and the unstable one. This splitting has to be invariant by the derivative of the flow. So when I put a T here is because I'm looking at the flow generated by the vector field. So we look at the flow generated by the vector field. We look at the differential of it. This differential acts on this bundle, and we hack that this bundle are invariant. And then once again, the stable is uniformly contracted and the unstable is uniformly expanded. So the picture we need to have in mind about the local behavior of an Anosov flows is like that. You look at an orbit, and in the neighborhood of the orbit, in the unstable direction, the other orbits are going away. And in the stable direction, the orbits are going closer and closer, exponentially closer. And if you take some orbit which is not in the stable or the unstable, it started to go closer and then it goes further on escape. So these Anosov dynamics has very nice properties, topological, like structural stability, and ergodic one, very good measures, and so on. But an important thing also is that there exists. So what are the main examples? So for Anosov diffeomorphism, the situation is a little bit strange because, yes, we have example. The most known are the linear automorphism of a torus. So you take a matrix in GL and Z, which is hyperbolic. That is, you do not allow any eigenvalue with modulus equal to 1. So you have an hyperbolic matrix with entries in Z, and also the inverse with entry in Z. And so these acts a priori on Rn, but at its leaves Zn invariant, you can look at the quotient, and the quotient is the torus Tn. So you get a diffeomorphism on Tn, which has a direction which are contracted and other which are expanded. The contracted are the one corresponding to the eigenvalue with modulus less than 1, and the expanded as the one with modulus larger than 1. So this linear automorphism on Tn has been generalized on nil manifold and infranil manifolds. Like you take a Lie group and you look at its Lie algebra, you take an hyperbolic element of this Lie group, and you consider an invariant lattice by this element. So you can take the quotient of your Lie algebra by this lattice, you get a compact manifold, and then your element acts on this compact manifold as an Anosov diffeomorphism. So, okay, that are the main examples. And for the moment, the results are for telling that they are mostly the unique one. That is, if you look at, for example, this theorem by Neuhaus and Franks in the 70s, they say that if one of the stable or unstable bundle has dimension 1, so we call that a codimension 1 Anosov diffeomorphism. So if you have a codimension 1 Anosov diffeomorphism, then indeed the manifold was a torus Tn, and your diffeomorphism is topologically conjugated to one of these linear automorphism on Tn. So for getting this result, you have to put together the result of Franks and the result of Neuhaus. One proves transitivity, and the other proves the conjugacy with the conjugacy with the linear automorphisms. On another, in the same spirit, now if you allow any dimension of stable bundle on any dimension of unstable bundle, but you require that the manifold is one of these manifolds here, that is an infranil manifold. That is, you take an algebra, you take a lattice, you take the quotient, and now you are allowed to make further quotients, finite quotients. Okay, so you take any infranil manifold, then any Anosov diffeomorphism on such a manifold is conjugated to one of these algebraic examples here, that is given by an hyperbolic element of a Lie group. Okay, what we know further? First, there is no other examples, and it's just a lack of example. That is, we don't know at all if there is something else. So we don't know if there are Anosov which are not conjugated to algebraic examples. And we don't know what manifold admit Anosov diffeomorphisms. Mostly we don't know almost nothing. There are recent there are results by Andrei Gogolev. We will speak here, but there are all the results I know are very, very partial results. Like if you want to know the dynamical properties of your Anosov diffeomorphisms, well, the most basic one is if the dynamic can split in pieces or not. And we don't know if Anosov diffeomorphisms are transitive. the algebraic one, yes, are transitive, but as we don't know if they are the unique one, we don't know if there are non-algebraic, non-transitive Anosov diffeomorphisms. So that is one of the most elementary questions we ask to dynamical system, and for Anosov diffeomorphism, we just don't know the answer. Now let's go to Anosov flow. So now we have also the example we have in mind when we study Anosov flows. And the two examples are the geodesic flow of manifold with negative sectional curvature, that is the origin of this Anosov flow, which are the objects that Anosov was studying when he defined the structure. On the other, if you take an Anosov diffeomorphism on some manifold, and you make I think the topologist for the manifolds speak on the mapping torus, that is, you take your manifold, you make the product by 0, 1, and you take the side 0 with the side 1 by your map. You get the mapping torus of your map. On this mapping torus, you have the suspension flow, which is what was the horizontal flow in your product. You take the horizontal flow in your manifold times 0, 1, but when you glue it, you recover the dynamic of your map. So you get an Anosov flows, which has mostly the dynamic described by your Anosov diffeomorphism. Is there something else? Well, in dimension 3, there are plenty of non-algebraic Anosov flows. What I mean by non-algebraic Anosov flows is Anosov flows which are not topologically equivalent to one of these two models, which are the suspension flows and the geodesic flows. So why are there so many non-algebraic Anosov flows? Why does that exist? Indeed, we have construction processes. We have two construction processes for building new Anosov flows, and we can build with some control of their properties. So it's possible to build Anosov flows with some strange properties sometimes. So this has been started by Handel and Thurston in 80, and then generalized by Goodman in 83. The same year, Fried gives his interpretation of Goodman surgery, but in fact, he did not prove that it was really producing Anosov flows, and that has been only done by my student Mario Shannon recently in his thesis in 2020, when he proves that, in fact, the Fried surgery, if you take an Anosov flows in dimension 3, a transitive one, and if you make a Fried surgery on a periodic orbit, you recover the Goodman surgery on the same flow. So you get an equivalence between the Goodman surgery and the Fried surgeries. Let me explain this surgery, which is a very important tool for Anosov flows in dimension 3. So you start with some Anosov flow on a 3 manifold, and you consider a periodic orbit. Then you make a blow up of this periodic orbit. What means to make the blow up is that you replace any point by the set of unit vectors, so the circle of unit vectors which are orthogonal to your orbit. So you look at the normal bundle of your orbit, and inside this normal bundle, you look at the unit vectors. So you get a circle, so you replace each point of your periodic orbit by a circle. What you get is a torus. well, if you, I am assuming the manifold to be orientable. So you get here a torus, and if you look at the stable and unstable manifold of your periodic orbits, you get now stable and unstable manifold here, which draw on your torus some new orbit. So your orbit is a torus on which you have 4 periodic orbits. Okay. The circle corresponding to the normal bundle of the points, that is the blow up of a point, we will call that the meridians. On the trace of the stable or unstable manifold, draw here parallel circles, so we all call them parallels. And now what consists the surgery? It consists to change the meridian. So you choose a new circle, which is one old meridian plus some numbers of parallels. So it's something making one turn in that direction on some number of turns in this direction. And you make a foliation by this circle there, and you collapse them. So you decide that now these purple circles are now your points. So you collapse them in points. And so as you make a foliation here, you get a circle of these points. So you get a new periodic orbit, gamma. And you get a new manifold with a new flow. And that is called the manifold, the flows obtained from X by Freed surgery along gamma with, you have to say what are the number of parallels that you add to the meridian. The fact that the new flow, so Freed noticed that the new flow is a topological Anosov flow, and the fact that it is a true Anosov indeed is due to my student Mario Shannon. Okay. So now if you have just one Anosov flow on one periodic orbit, you get infinitely many new Anosov flow on new manifolds. So you can build like that infinitely many Anosov flows starting from 1. And so we can look at the set of Anosov flows, more exactly of the equivalence class, topological orbital equivalence classes of Anosov flows. You can look at that like a graph. If you put some je sais plus comment on dit bridge between two, you put a segment between two classes if you go from one to another by a surgery. And the question is that set connected? So is any Anosov flow obtained from some algebraic one by surgery in dimension 3? Certainly not if it is not transitive, so we have to put the word transitive. And so that's a question which is open, and there are people working on that, and there are partial results on like this very nice result by Pierre de Hornoy, we will speak in some days, on once again Shannon. They prove that if you take the geodesic flow of any hyperbolic orbifold in dimension 2, so you get an Anosov flow in dimension 3, and so it is equivalent by surgery to the suspension of this Anosov matrix to 111. Okay. Now there is this first surgery process for building Anosov flow, and there is another one with a different flavor, which started with Franks and Williams in 79, and then I think it's not 84, but it's 94 by myself on Langevin. So that is a 9. Then we finished to build it in some years ago in 17. So what I've done, Franks and Williams, is to build an example of a non-transitive Anосov flow. In 94, with Langevin, what we have done, answering a question of Thierry Barbeau, Fenley on exchanges, was to build an Anосov flow in dimension 3, which admit a torus which is transverse to the flow. And there is exactly one periodic orbit which is not cutting this torus. So the flow is not a suspension. And in fact, when we make that, it was clear that it was a more general process of construction. And we have made it with François Béguin and Bignu. So here we built many manifolds for example, manifolds having an arbitrary number of non-equivalent Anосov flows, some of them transitive, some of them non-transitive. So, okay. So we have now a technology for building Anосov flows in dimension 3. And this technology consists in considering what we called hyperbolic plugs, that is manifold with boundary, which has some entrance boundary, some exit boundary, and to glue the boundary together with some transversality condition, and we can get Anосov flow by this transverse gluing. In what will follow, the Franks and Williams example will be very important, so I will give some detail on the initial construction by Franks and Williams. So let me present the example of non-transitive Anосov flow by Franks and Williams in 79. So they started with any hyperbolic matrix acting on the torus T2. So you get an Anосov diffeomorphism there. And then, as explained by Smail in his famous paper, they make the operation called derived from Anосov, that I will write as dA. So in what consists to do a derived from Anосov is that you have an hyperbolic set. So here the hyperbolic set is a whole torus, and you look at some periodic point, let's say fixed point. And now you look at this point, and in a very small neighborhood, you will multiply your diffeomorphism by a diffeomorphism which is contracting in the unstable direction. It will, we want that it preserve precisely the unstable foliation. So we multiply by a diffeomorphism which keep invariant every unstable leaf, but which is contracting exactly in a neighborhood of the fixed point that you want. So this point will bifurcate. You get a flip, no, not flip, not saddle node exactly, but you replace your point when in its unstable manifold. So it was a repelling point, and now it is replaced by 3 points, 2 repelling and 1 attracting. So in the ambient manifold, it was a saddle. So you keep, as you keep exactly the unstable foliation invariant, you keep exactly the stable eigenvalues. So now you have replaced your saddle by 2 saddles on 1 attracting point. So in fact, all looks like you open the stable manifold of the fixed point, you open it, you make a hole inside, and the hole is the basin of an attracting point. And now, if you look at what is the non-wandering set now, initially it was the whole torus, but now it is exactly the complement of the of the basin of your attracting point, and the maximal invariant in what remains is an hyperbolic repeller. Is a non-trivial hyperbolic repeller. Okay. So what they start with Franks and Williams start with the Anosov on the torus. They make a derive from Anosov, so they get an attracting point. Now they make the suspension of this new diffeomorphism. So they get a flow on the mapping torus of the Anosov map. And so for this flow, they have an attracting periodic orbit. Okay. As it is an attracting periodic orbit, you can draw here a circle with a dynamic going inside. And when you look at the flow, what you get is a torus transverse to the flow. So you get a torus transverse to the flow. So now you cut the manifold along this transverse torus, and this transverse torus is cutting a tubular neighborhood of your periodic orbit. So you remove this, you delete this tubular neighborhood, and you get a manifold with boundary with a flow which is going outside because it was going to the attracting set, but the attracting set has been deleted. So you get a flow which is pointing outside the boundary of your manifold with boundary. Okay, so you get now a manifold with the boundary is a torus, and you have your vector field which is pointing out of your manifold through the boundary. Now you make the double of your manifold and do it with your flow. That is, you take another copy of it. You keep the manifold unchanged, but you change. That is a minus. You change your flow by putting minus the flow that you just created. So here you have a flow, and here you have minus this flow. It's the same manifold, but I look at in a mirror. Okay. So as the vectors are going outside here and inside there, okay, making a change of coordinate, I can assume it's orthogonal. So if I glue them by a diffeomorphism, I obtain a new flow on the manifold, which is the double of this manifold with boundary. Okay, so now the important thing is to understand what are the foliations, what are the hyperbolic data that we have on the boundary. On this side, I had a repeller. So a repeller has an unstable foliation, and the orbits are going outside the manifold. The orbits which are not exactly on the repeller are going outside the manifold, and so their unstable leaves induce on my torus a foliation. And so it's not hard, and I did not make the picture, so I will not explain too much, but it's not hard to see that when I have made exactly this derived from Anosov, keeping precisely the unstable foliation, and so removing here some tubular neighborhood of my periodic orbit, what I get on the torus is, so the torus, I draw it as a rectangle, so you have to imagine this side glued with this one and this one to that one, okay? So what you get is two web components. So the circles correspond to the unstable manifold of these two orbits. So this unstable manifold on that one, so that is for the diffeomorphism, but you have to make the suspension. Draw on the circle on the torus, draw two circles, so which are these two circles there, and all the other leaves are going from one to the other. When you make the double, you get the same drawing. I changed a little bit. It's the same drawing, but I changed the position of the rectangle. It's just I switch a little bit my rectangle so that I see the two circles in the middle, because that allows me to put them together here and to see that they can be put in a transverse position. So it's exactly what has done Franks and Williams. So that is, they took here the suspension flow, they remove the tubular neighborhood of the attracting periodic orbit, they get a manifold with an exit vector field, they make the double, and they glue in the way to get transversality of the unstable foliation on that torus with the stable foliation on this one. And this is enough to ensure the hyperbolicity, the global hyperbolicity, so the fact that the flow they built will be Anosov, and it's no more transitive because all the orbits are going from here, the orbits which are going from here to there never go back because there is only one boundary component and everybody is entering there. So he broke the transitivity. So with that, they built a non-transitive Anosov flow in dimension 3. So in the same papers, the Franks and Williams claim that, in fact, they could do non-transitive Anosov flows for any dimension of stable and dimension of unstable larger or equal to 2. So if you just require that the stable has dimension 7 and the unstable 13, so they get a non-transitive Anosov flow with a stable dimension 7 and unstable 13. And their idea was very simple. What they do is they consider the construction in dimension 3, the initial construction we just have seen. They multiply the derived from Anosov F0 by a linear Anosov map with the dimension they wanted -2. So they look on this torus of dimension S plus U -2. They look at a linear Anosov map. Okay. They make the suspension of this the new map, the product of F0 by FB, the direct product. They make the suspension. They make they remove the attracting torus, and they get a manifold with boundaries. They make the double, and they claim that you just have to glue that in a transverse way for getting your Anosov flow. So, in fact, the Anosov flow they get is a skew product over the dimension 3 example. I mean, they have a manifold, which is a fiber bundle with fiber, this torus of dimension S plus U -2, and their flow is projecting on the flow of the non-transitive Anosov flow in dimension 3 they just built. So when I was in Penn State working with Thomas Barthelme, so I didn't know that they claim the existence of Anosov flows in any dimension with any dimension of stable or unstable. And so Thomas told me, so I was thinking that there was no example, non-algebraic example in dimension larger than 4. And Thomas told me, no, Franks and Williams have done examples indeed. And so I look at their construction and I try to extend it. And each time I extended it, it was too easy to extend, and it was proving stupid things. So at some moment, we had a true look to the construction, and in fact, it cannot work. So we first show that it cannot work. So if you look at an Anosov flow in in higher dimension, and you assume it's a skew product with some fiber, which is a torus, over a three-dimensional Anosov flow, an Anosov flow in a three manifold. Then you have two possibilities. Either the Anosov flow on the three manifold was a suspension flow, and so indeed your flow was a suspension flow by a product of a three-dimensional matrix by a higher dimensional matrix, or you need to have the two dimensions to be equal and indeed larger than three. We will see, indeed, I think that in the second part do not exist, but we were not able to prove it. We only get the conclusion that it has to be equal dimension and larger or equal to 3. So the statement they had just cannot work. And the reason of why it cannot work is that it's in the result of the 90s by independently by Sergio Fenley and Thierry Barbeau, looking at the structure of Anosov flow in dimension 3. So what we can see on their work, it is not stated, but it's clear in their work, that if you have an Anosov flow which is not a suspension, then you always have two periodic orbits, with one is freely homotopic to the opposite of the other, to minus the other. So maybe I will go fast because my time is flowing, but let me explain why that is that concludes that the two dimension has to be the same. So if you assume that you have an Anosov flow Y, which is a skew product over an Anosov flow in dimension 3. So you have these two orbits, one homotopic to the inverse of the other. So in particular, if you look at the vibration over these two periodic orbits, the monodromy of this vibration by torus over one is the inverse of the monodromy of the other, because one is homotopic to the inverse of the other. So, but these homodromies, so these over periodic orbits, the fact that it is a skew product makes that the vibration over this periodic orbit is invariant by the flow. On the monodromy is the first return on a fiber. So in fact, on the monodromy, you can see the stable direction and the unstable direction. This implies that the monodromy was by Anosov diffeomorphism on the fibers, and that the bundles on the fibers are the eigendirections of the monodromy. But if one is the inverse of the other, it exchanges stable with unstable. So you need to have the same dimension of stable and unstable. Okay. The fact that the dimension has to be larger than 3, it's more difficult, so I will not explain. Let me go to our construction in the 5 minutes, in the 5 remaining minutes. So Franks and Williams use the three-dimensional example for extending it in any dimension by skew product, and it cannot work. What we have done is not using the example in dimension 3, but remake exactly the same construction as they have done in dimension 3 to adapt it in any dimension. So the first things we have to adapt is the derived from Anosov operation. So in fact, when you have a flow on your, let's say, an Anosov flow, and now you look at a compact manifold, which is invariant by the flow, a submanifold, and we assume that, so if it's you have a compact invariant manifold, you can, and it's an Anosov flow, it has a stable and unstable manifold, and we assume that the codimension of the stable manifold is 1. So I have this submanifold here, and it's stable manifold, and as it is, it's stable manifold. Normally, it's an unstable direction. Yeah, there are only unstable directions, so it's normally expanding. And we can repeat the DA operation, opening this stable manifold and creating a copy of my invariant manifold K, which will be an attracting set. So I will have an attracting submanifold here, and this stable manifold is be opened in two stable manifold of two saddle-like invariant submanifold K1 and K2. Okay, so that is the DA operation. So this DA operation creates some attractor K0, and as it is an attractor, you can look at a tubular neighborhood, and the boundary of a tubular neighborhood will be an hypersurface transverse to the flow. And this hypersurface is like the unit normal bundle of your submanifold K. Okay, so you have a submanifold of codimension 1, which is transverse to the flow. So you can cut your manifold along this hypersurface sigma on removing the tubular neighborhood of K0, and you get a new manifold M plus with a flow X plus, and with the boundary transverse to the flow, and your flow is pointing outside. And then you can make the double. You keep the same manifold here, but you choose the flow to be the inverse on the other flow. And so you just have to glue them together. And if you are lucky, if you succeed to glue by something which sent the unstable foliation here transverse to the stable one there, you are done. You get your Anosova flow, non-transitive Anosova flow exactly as Franks and Williams has done. The difficulty is that here, the stable manifold that you want to make transversal is exactly the hold unstable one, because you just remove the sign of your flow. So what you have to get is some phi which sends this foliation transverse to itself. So that's the difficulty to get that, because you have some constraint due to the topology of your boundary. So that is a topological problem. And so what is the solution? The solution is that we start with an hyperbolic manifold of some dimension. We look at its geodesic flow on the unique tangent bundle of it. And now we consider a totally geodesic codimension 1 submanifold. Okay, so if you look at as it is totally geodesic, it's invariant by the geodesic flow. And if you look at its tangent bundle, it's a codimension 2 submanifold invariant by the flow. Okay. And if you look at its stable and unstable manifold, there are codimension 1 submanifolds. As there are the stable manifold is codimension 1, we are allowed to perform the DA operation. So we get the attracting copy of our manifold on the surface. We get a manifold transverse to the flow, where our flow is pointing outside. Okay, but now we want here to get something which sends the foliation transverse to itself. And that is the interest to look at geodesic flow, is that if you look at the geodesic flow, it has a symmetry. We just send the vector on minus the vector. So this vector sends the geodesic flow in minus the geodesic flow. It keeps our totally geodesic manifold invariant. So the unit tangent bundle of our totally geodesic manifold is invariant. The tubular neighborhood is invariant, so our section is invariant, but it sends, as it sends the flow on minus itself, it sends the unstable foliation on the stable one. as it's saying the unstable foliation and the stable one, it's sent, in fact, so our unstable foliation is set on the stable one, but which is now the unstable of the other side that is transverse to the stable one, and we get the transversality. So we get the Anосов flow. We can also get transitive Anосов flow if we repeat the operation along two. If we start with not just one totally geodesic manifold, but two of them, and we do the A in the stable direction and the unstable direction, we can get transitive Anосов flow in higher dimension. Okay, so now we started a building process in higher dimension.
Christian, I'm sorry to interrupt you. We have 10 minutes before the beginning of the next talk.
Yes, I will just stop now. I just finished. Thank you. So let me just put the questions that I think are interesting. All our example, and it's crucial for our example, the result as a closed manifold which is transverse to the flow, and we don't have any process. So they are very specific. It's not the usual Anосов flow do not admit a transversal, which is a closed manifold, but all our examples are like that. Also, our example has always the same stable and unstable dimension. So we don't know if it is possible to break this equality here. So our process is very like what I have done with François Béguin and Bignu of gluing hyperbolic plugs. But there is a very interesting other process, which was the Handel-Thurston-Goodman-Fried. What could be an equivalent there? It would be very crucial to do that. And let me remain just for finishing a very old and classical question. We don't know about codimension 1 Anосов flow if they are all suspension. So what we know if they are transitive because of the work of Berezovsky, and Asaoka proves that indeed they are equivalent to some volume preserving one, but we still don't know if they are suspensions. So let me say a word more about the math and community. I look very strange that a famous paper of 79, that is more than 40 years ago, has been found to be with a big mistake 40 years after. And I think that is a little bit because people, when they see a counterexample, just look at, oh yes, it exists, and do not care about how you do. And it's not just a mistake by Franks and Williams. I think it's a mistake on everybody which care about Anосов flows of not having a look to their construction, because the mistake was easy to find. So I think it's a shame of all of us to leave this mistake during 40 years. So I hope that someone will look at our example, and it's not in 40 years that someone will tell us that it was wrong also. Thank you.
Okay, thank you very much. So I think maybe we will skip the questions to allow people to have a 7-minute break, and we reconvene at 6 p.m. Moscow time. Thank you again, Christian.
Жень, у тебя что-то со звуком. Жень, Жужома. Это Жужома пытается сказать.
Hello, Federico.
Hi, Christian. Hi, Andre.
Hey, Federico, how are you? Good morning.
Yeah.
I just see the title. Codimension 1, Anosov diffeomorphism. Yeah. By the way, do you know if there is any progress about codimension 1 Anosov flows?
Not that I know. It would be nice.
Excuse me. I would like to ask, but I not switch on my sound. Christian.
I'm listening.
What you call algebraic Anosov flow? What is mean algebraic? Repeat once more.
Algebraic Anosov flow is topologically equivalent to either suspension or geodesic flow.
Okay. So is it, I am understood correctly that, do you know example by Williams Robinson in pretzel that is not structurally stable? We glue in 2 derived from Anosov. And it's not possible to construct structurally stable. But your example, you have suspension on these examples and construct Anosov flow. Is it true?
So the
Because
example was for
your foliation are transversally, yes?
So the example you speak are for diffeomorphism, yes?
Yes, but it's not possible.
Okay, so that is not possible to make it structurally stable. Okay.
Yes.
But Franks and Williams have done it for flows, and yes, it's structurally stable.
Okay.
But it's not suspension, Slava. It's not suspension.
Yes. I would like to check that I understood correctly. So if we take suspension, is it possible to construct Anosov flow? Yes. Okay.
No, it's not suspension.
It's interesting for all the yes or that.
But Christian, if I right understand, it's not suspension from Robinson-Williams example.
No.
So they take the suspension of 2 DA derived from Anosov. They remove the attractors, and then they glue 2 copies.
But you can go by such way, do connected sum of derived from Anosov. Like
it's not connected.
It's suspension, but
it's connected it's not connected sum because it's not on.
It's more difficult
sphere, but on a torus.
Yes, I understand. But you can go like this. Do connected sum by 2 torus with 2 torus and after that.
No,
because the gluing is not like that. You have to reverse something so that is not a suspension of a gluing. It's a gluing of suspension, it's not a suspension of a gluing.
Yes.
It's not commutative.
It's not commutative. Indeed, I understand.
We have to leave Federico.
Good constructions. Thank you very much.
But indeed, I don't understand what is mean Goodman surgery. Indeed, I tried to understand, but I don't understand. We have a time now, not?
Sorry?
I don't understand Goodman surgery. I don't understand. No, yes. But we have a time, we have a break now.
We have a break?
We have 3 more minutes.
3 minutes.
3 minutes. Yes. I can understand.
Thank you very much.
So Federica, am I right that you talk on the whiteboard behind your back?
Yeah, exactly. So you can pin the screen and then it will.
Okay.
Я хотел спросить.
Zoom wanted to ask me by phone and wanted to ask Christian. Christian, I can ask you. I am sorry. Then why when we get when we do Goodman surgery and the algebraic Anosov flow, we get not algebraic Anosov flow. Why after Goodman surgery we get non-algebraic?
We change the manifold, so the manifold is no more.
No more admissible to algebraic. Yes. Like
yes.
This?
If we start with the unit tangent bundle of a surface, you do the surgery and you get a manifold which is no more
admit algebraic. Yes.
No more a circle bundle. It can be an hyperbolic manifold after surgery.
Yes, I understand. I translate to Jujon. Thank you, Christian.
Okay, so let me remind everybody to mute the Zoom. And it's a pleasure to introduce our next speaker, Federico Rodriguez-Hertz from the Pennsylvania State University, who is going to talk about smooth conjugacy for codimension 1 Anosov diffeomorphisms.
Okay, thank you very much for the invitation to speak in this conference. It's really an honor and a pleasure. So I will talk about Anosov diffeomorphisms and their smooth conjugacy class. So this is a joint project with Andrei Gogolev. We started to try to discuss actually smooth conjugacy for Anosov flows, but well, of course, in trying to prove something, we first went to expanding maps, and now we are doing this codimension 1 Anosov diffeos. And hopefully I will be able to say something about how this relates to flows as well. But let me start a little bit about the basics and definitions here. So the standing setting is an Anosov diffeo. I will not define it, especially because Christian defined it half hour ago or so. But the two important objects here will be both the unstable and the stable bundle for our diffeomorphism. So F will be CR. We will have to discuss about R later. So typically it will be at least 2, sometimes it will be 3 or 2 plus something to make the theory work. Now, as was already said, these diffeomorphisms are structurally stable. That was part of Anosov first contribution to Anosov systems. And this is about the topological conjugancy of them. So let me just put the basic definition. So F I are topologically conjugate if there exists H homeo such that H compose F1 is F2 compose H. Okay, so that's after a topological change of coordinates, we get that both guys looks the same. Okay, so that's structural stability. Essentially tells that in the neighborhood of F. So here M1 will be equal to M2 in this case, and then F2 is a perturbation of F1, and you get always this conjugacy. Now I want to discuss a more defined notion of equivalence, different from topological conjugacy, which will be very much related to this smooth conjugacy. Okay, so whether this smooth conjugacy, whether this conjugacy is smooth or not, is the topic of the talk. But before getting to that, I want to define a different notion of equivalence. And I think it's a very reasonable notion of equivalence, especially due to the fact of how we in general look at the systems. So when we look at the system, we typically don't see it directly as the dynamics itself, but through an observable. So now we are given a second data, which is a function phi from this one that I'm not open yet. Phi as smooth as the map, so the observable I want it to be smooth. And let's say R is at least 1, even though that for definitions is not so important. And I want to look at equivalence for the pair, F and phi. So not just that the dynamics looks the same, but that the observable is giving me exactly the same information. So let me write down this definition. Given a pair Fi by I 1, 2, we say F1 by 1 is equivalent to F2 by 2 if there exists H from M1 into M2 homeo such that H compose F1 is F2 compose H, and U from M1 to R such that the observables are homologous, so are really giving us the same information. So when I do phi 1 minus phi 2 compose H, I get U compose phi 1 minus U. And actually, I will let myself a constant. So this slide I want continuous. And see. So this equation is some sort of cohomological equation for this function phi 1 minus phi 2 compose H, and this is telling us that this function, this difference, is homologous to a constant. So, I'm keeping here the conjugancy, so the equivalence, in a very low regularity, so just C0 for the conjugancy and just continuous for the U. But still, I want to try to convince you today that this is way stronger equivalence than the equivalence for just the dynamics. So trying to see the same thing through two different observables will be one step more complicated than just trying to see the same dynamics when it comes to differentiable versus Z0 business. So, let me now move further about, let me talk a little bit about, maybe let me just start stating our results, and then maybe I can say a little bit more later.
Federico, could I ask you a question?
Yes.
In the example that motivated this definition, what is
Yes.
phi1 and phi2?
Okay, good. Actually, this was exactly what I was going to do in the next theorem, which was this example.
Okay.
But yeah, maybe let me just answer it to you before I say the theorem. So in the motivating things, the phi I will be really very much attached to the f, and the phi I will be log of the Jacobian of the function. Of course, in the volume preserving, this is just constant. And then the equation I wrote is telling you nothing because constant is equal to a constant up to a constant, and nothing happens. But when this f is not volume preserving, this function is actually very nice, moving, and this is going to give us a lot of information. So let me state the one of the theorems we prove. So let A in SL3Z be a hyperbolic matrix actually it's a corollary of our results, but I think it reflects very well what we are trying to do. And assume it has two complex eigenvalues. So the pair of complexes. Sigma, sigma bar, modulus of sigma larger than 1. And then the other will have to be smaller than 1. Then there is a neighborhood just for brevity, there is an open and there's subset of a neighborhood U of a neighborhood of A, and maybe let me just see one neighborhood is enough, such that if F1 and F2 I in U, Fi are at least C3. Actually, C2 plus something will be enough, and let me put C3 for brevity. And F1 log Jacobian of F1 is equivalent to F2 log Jacobian of F2, then F1 and F2 are smoothly constant. Okay, so that's pretty much the main statement. The open set U actually is quite reasonably expressed, so it can be characterized through the eigenvalues at different periodic points. So certainly we will not want the guy F1 or F2 to be volume preserving, because in this case this guy will be just 0 and there is not much information, so we don't hope this to be true if the F1 and F2 are volume preserving. So that will be one condition. So in this neighborhood, in this open and then subset of the neighborhood of A, there will be no volume preserving guy at all. And we will also need to assume some genericity property for eigenvalues for some of the of the periodic orbits. And that's pretty much all that is needed to know for this FD. And that's pretty much enough. Now that's about the density. So what we are leaving outside of this neighborhood of A. Now, how close you need for the neighborhood U? Well, the point of having this linear guy and being perturbation of the linear and having this sigma bar, sigma conjugate on the unstable is that the dynamics on the unstable is conformal. And then we want perturbation of these conformal dynamics along the unstables. And the main point here, now I probably can go back to what I said about unstables, is about smoothness of ES and EU. So that's why these two bundles are, as always, so important in this part of the theory. So this is something that was extensively studied by Anosova also. He gave several examples of non-smoothness of this ES and EU and some very explicit bounds on the regularity for these systems. But in the conformal or close to conformal situation, actually these bundles are smooth. So the same as these bundles are C1 plus almost actually plus sigmund, so it's almost C2 but not C2 and not C1 plus Lipschitz. In the case of one-dimensional dynamics, in this case of higher dimension, and that's why we want the dimension of the manifold to be at least 3, these bundles become a little bit better on their smoothness. So we have two bundles. I'm only assuming that the dimension of ES is 1, so the dimension 1 is for the dimension of ES being 1, and the dimension of EU is, in this case, 2. So, so how this affect the business is that both the stable bundle and unstable bundle are actually C1, and actually the unstable will be C2, but that will be discussed later. Now let me give you a slight proof of why the stable bundle is C1. I'm sorry, the unstable bundle is C1, and that's just so this is stable, this is stable. Take here unstable foliation. This. You have this unstable holonomy here, guys, and you have this holonomy map, which is sliding along the unstables from this line, which is a stable manifold, into this line, which is a stable manifold. Now, Anosova proved that this foliation is actually absolutely continuous, and actually his proof is very explicit and computes the Jacobian of this absolutely continuous function, and this Jacobian is nothing but the derivative once this guy is one-dimensional. So this is giving you a very explicit formula for the derivative. I'm showing that why this unstable foliation is C1. Now, why stable foliation is C1 is a little bit more complicated, because now we are looking at this vertical holonomy from unstable to unstable sliding along stables. And now, of course, Anosova proof of absolute continuity tells you that this Jacobian exists, it's beautiful, it's continuous, but this is only telling you that you are sending Lebesgue measure here into something equivalent to level measure, but under some very beautiful Jacobian. But that's not enough for being C1, that's just good enough for being absolutely continuous. What you have to show is that if you take a small disk here and you map the disk here, it actually goes into some small disk here. So that will be Lipschitz, but if you do it carefully, you will get at least C1. Now, the reason why this is working, and this comes from this conformality there, or close to conformality, and actually is a competition against the distortion of disk along the unstables versus the rate of contraction along these tables here. So the proof of by Anosova of this, maybe by Anosova and Sinai actually, by now, of this regularity of this holonomy is you go to the future, these tables get contracted at some speed. Now these two guys get very, very close one to each other. Now these disks, after distant integrals, grow and get distorted. So due to the lack of conformality along the unstables, I'm already perturbing, I'm nonlinear, so the guys stop being fully conformal. But still, if I took this very small, this will get some sort of ellipse with the eccentricity of the ellipse controlled due to the fact that I'm being close to conformal. And now the question is how close these 2 points get versus how distorted or how eccentric these ellipses become. And well, this is a competition that if you are close to conformal can be very well written, and you get the regularity of these tables, of this stable foliation. So let me write down the actually one of the optimal numbers coming from this file I wrote. So it's just true for any dimensions. As I said, that's essentially already happening in earlier work of Anosova in the 70s, and it has been extensively studied after. There is some very important work by Hasselblad on this matter as well. So let me just go a little bit further on this Anosova thing. So I have 4 constant, lambda minus, lambda plus, and mu minus, mu plus. And okay, now I will need to really use this stuff. So I want, there we go, the norm of DFB to be between lambda plus and lambda minus norm of B, and this is for B in EU. And what I'm doing now is in any dimension, so it's some old known result, but I think it is really important if you haven't seen it. And people forget about this. Minus inverse and plus inverse of B, and that's for W, it's norm of W. And that's for W in ES. So this is saying that along the unstable, the expansions are between lambda minus and lambda plus, and along the stable, the expansions are between mu minus and mu plus. So lambda plus is larger than lambda minus, larger than 1, and mu plus is larger than mu minus, it's also larger than 1. So that's why putting the inverses there. And then we have this quantity is log lambda minus divided by log lambda plus log mu minus divided by log lambda plus and du of f, which is log mu minus log mu plus log lambda minus divided by log. So it's symmetric with respect to the use of inverses, and the main point is that is very as I said, essentially this goes back to Anosova later on by Hasselblad. So this is that the ES bundle is CBS of F and the EU bundle is. So that's the regularity, and these numbers are always positive. That's guarantee you at least the regularity, but depending on the features of your particular system, these guys can be very, very large, essentially. So, of course, not infinity. Yes.
Oh, sorry to interrupt you. It's a little bit difficult to read the superscript.
Okay.
Could you just read out aloud?
Yes. So
what is S and what is U?
Yeah. So one is S and the other is U. So the PS bundle, actually, let me just put a sigma. So the E sigma bundle belongs to C B sigma, for sigma equals to S and U. So is this any better? Yep.
Yes, and on the left side of the blackboard, what is BS and what is BU?
Oh, okay. So this is.
Thank you.
The other one is S and the down is U. So it's just. So this is just reflecting what I wrote. So you go and write down the computation I did, and of course you do it with all the details. And that's the competition of the eccentricity along one direction versus the rate of contraction along the other direction, pretty much. So that's the yes. Okay. So
thank you.
Our assumptions on conformalities will essentially imply that these sigmas are large. So we need actually to have the bundle smooth. So our theory so far is not working if these bundles are not smooth enough. Okay, so that's the first thing to notice. So now let me give you the second ingredient we need in our theory. So one was smoothness of bundles. Second is what Katok called periodic cycle functionals. Periodic cycle functionals. So this is a notion introduced by Katok. If I understand correctly, and it detects the fact of the cohomology essentially of the equation that we've discussed already a little bit of this equation. So is the defect to solving this equation. That's what it does. So let me define it. We are given a point P. We have some stable manifold, some unstable manifold, some stable manifold, and then you close it with unstable. Actually, you could put more legs, but I will just stop in these 4 legs. And then if we call this loop gamma, this SU loop, and psi goes from N to R. Then you look at how bad could it be if this guy is or is not homologous to constant by summing up along stables and some along unstables. So you do the forward guys. So P is x0, this is x1, this is x2, this is x3, and you do some on the future orbit. So assuming at least that was psi, sorry. Assuming psi was Hölder, this sum is convergent. Now same thing you do for x2, x1, and then you sum for the negative iterates fn x2 minus psi fn x1, and for reasons that I will not write, but I will say, you put a minus sign here, and then you add and subtract the other two legs. Now, why I'm subtracting or adding here essentially is because if the function psi were like the phi homologous to constant, when I do this sum, what I'm getting is exactly u at x1 minus u at x0. And then here I want to have exactly the same, but since I'm going to the past, then this equation gets a little bit twisted to the other side, and I still want to get ux2 minus ux1, so that the x1 here will cancel out. And if the function is homologous to constant, then when I do these sums, I will have to have a 0. And what Katok and Kononenko prove in the setting of partial hyperbolic system, but this of course also holds for Anosov, and it's much simpler in the Anosov situation, is that if you have vanishing of these guys, of these sums here, so this total sum is called PCF gamma of psi. So this is TI by Katok and Kononenko. It's a particular case, a very simple case. Is if PCF gamma of psi is 0 for every gamma, then there exists U Hölder, psi needs to be Hölder, such that U minus U composed F equals to psi plus the constant. So this guy really is detecting the cohomology. So these objects are really detecting the cohomology of the system. Now, the importance of these guys is the following in our setting. So I can put here a parameter for this gamma, which is this point P, and allow this guy move with P. Okay, and I can move P along a stable manifold or along an unstable manifold. And what I'm trying to know is the regularity of this PCF gamma P as a function of P. So that's the game we are going to play. But before that is, why do I care about this? The reason I care about this is the following. So if I have these two Anosov system with these two potentials phi 1, phi 2 being equivalent, then I take a periodic cycle function for one guy, for a curve gamma, for the dynamics F1. Let me just put here. So this is to emphasize who is the dynamics. And then I map the conjugancy gamma to h of gamma. So since stable goes to stable, unstable goes to unstable, and for this definition, really it's not the curve, it's the 4 points which are the relevant guys, then we can, it makes sense to consider these two things. gamma. So if these two guys are equivalent, then these two guys happen to coincide. And of course, I have to, yes. Here, what is very important is this guy here and this guy here. So here is gamma, and here is this H of here is P. Okay, so why this equality is really so important? Even though it seems to be very benign, it is very, very important. And the reason why this equality is just a very simple computation is you write it down, and it's the most natural object in the world, so you expect this to happen. So the fact that this implies what is important, but actually it is equivalent. So these two guys will be equivalent if and only if you have this same equivalent. That's pretty much yet the corollary of this Katok-Kononenko type of result. Now, the reason for this is that when I now start moving P, this H of gamma P actually is, you can think of this as gamma sub HP. I have this square for P, have the corresponding square for H of P. And now I start moving P. So what is this? This is a function that we just, for the sake of brevity, call it eta of P. And this is another function, eta 1 of P, and this is another function, which is eta 2 of H of P. And I get, by this equality, that these two functions coincide. So eta 1 goes from R to R, and eta 2, so eta I goes from M to R, or at least from a neighborhood. Eta 1 goes from a neighborhood of P into R, and eta 2 of H. And I have this relation, eta 2 composed H is. Now, the same computation, or very similar computation, not the same, that give me that the stable and the unstable bundles are non-trivial, are smooth, is going to tell me that this eta 1 is also a smooth function. And this eta 2 is also a smooth function. So I get these two smooth functions which satisfy this equation. So this should become reasonably suspicious to you. The fact that a homeomorphism is related in this way through smooth functions is something very, very hard. So a smooth function shouldn't be allowed to straighten out a homomorphism unless the homomorphism is already smooth. So, and the point is why this is true is because your smooth function eta 2, you can just think about a coordinate system. So it's just the projection into the second coordinate, or into the third coordinate, or whatever coordinate of your system. That's a typical, by the implicit function theorem, that's what a function into R do. You're looking at a coordinate. So what we are saying here is that in coordinates, this H of P is looking smooth. So it means that there is some smoothness of the H. Now, there is some trick from the fact that you have complex eigenvalues and everything that will tell us that once I have this, then I compose with F and do another trick. I will have that H actually have to be really smooth, completely. Just by picking 3 of these guys to get not just mapping to R, but into R3. And then inverse function theorem will tell me that H is smooth. Unless something really bad is happening, and the really bad is that I cannot use implicit function theorem, which would mean that this guy has 0 derivative. So it is smooth, but it may have 0 derivative. If it has 0 derivative, I cannot use implicit function theorem, and then our technology will not give us that this H of P is smooth. Now, what's the problem with eta 1 having zero derivative? Well, if this eta 1 has zero derivative, it's because when I look at this periodic cycle functional and I move the P, this guy has zero derivative. And I was not so explicit, so here P can be moved whatever you want. So I'm fixing these four guys here, and I'm moving the P. So I can't just, but it's not fully fixing, so I'm fixing this guy. This depends on the choice of P. And when I map this guy toward this point, this loop is shrinking, and there is clearly continuity. So when P goes to here, this periodic cycle function goes to zero. And if the derivative is zero, then I get that this is constant. And being constant and having value zero here means that this is fully zero. So at the end of the day, what I get is that if either I get some non-zero derivative for this guy or this guy vanishes. If this guy vanishes, then phi 1 is homologous to constant. That's one possibility. If this guy is not homologous to constant, then this guy has some non-zero derivative, and hence the H is. So that's essentially how the idea of how this technology is working. And then when you want to prove the case of log of the Jacobian, that's essentially what you do. So if this guy is not homologous to constant, which will imply in this case volume preservation, then I get smoothness of the H. And that's it. So I think I have 5 minutes. So that's was about how to use the technology and the proof. Let me tell you some limitations of this.
Oh,
now,
Federico,
yes.
you have 5 minutes.
5 minutes. Okay, good. Thanks. So there are 2 more situations of interest in this stuff. Maybe before going to the limitations, I want to mention this. So the 2 other important functions are the log of the unstable Jacobian and the log of the stable Jacobian. These are also 2 important functions here. And in the case of volume preservation, you go to restrict your attention to these 2 guys, which one is the inverse of the other because you're volume preserving. So actually it's just one of them, even though it seems that there are 2 of them. And then you look for the matching of this guy. And again, you get this sort of dichotomy, which is either this guy is constant or homologous to constant, in which case you get that the entropy maximizing measure is the same as the SRP measure. And since you are volume preserving, this is volume, so volume is entropy maximizing, or you get the smoothness of the conjugacy. So, so this is what you get. But I want also to make one more point in this picture of periodic cycle functional, because I think it's something not so well known, and it deserves to be known. So when I write down this ECF of log of the unstable Jacobian, or this loop here, so I'm fixing the P, I take X1 here. These are, in this case, in this picture, I think I'm doing, this is unstable, this is stable, and this is unstable. Then this quantity is a very known quantity, which is the Jacobian of this holonomy map, but not with respect to volume, but with respect to the conditional measure of the SRB measure. So that's essentially what it is. And actually the same is true if you take any potential phi. So pick any potential phi, look at the conditional measure of the equilibrium measure along unstables, and then this guy is the Jacobian of this holonomy when you send this conditional of the equilibrium into this conditional of the equilibrium. So it's just a very simple computation, but it's important in showing why these options are so natural at some point, and why this will be well behaved with respect to the equivalences we are discussing. Now, the problem in dimension 2 and why what I said is not working in dimension 2 is that these guys are Hölder for every Hölder, are essentially Sigmund, but they are not C1. And so, since they are not C1, I have that the two Sigmund functions and a function h that intertwine two Sigmund functions, and this is very complicated equation to solve. So you don't have implicit function theorem for Sigmund functions. And that's really the big problem in dimension 2, as well as dimension 3 for flows. So still, in general, for flows, and what is behind this problem here, and the equivalence relation I just defined, maybe this will give some light on what is this strange equivalence relation I was discussing. So if you have two flows, xi, xis, x1s, so this is the vector field, it is better, x to t. Then actually, again, in the case of Anosov flows, Anosov showed that these are topologically conjugate, but topological conjugacy is not resolving the time. So that's what happened in Anosov. Now, you can ask in the equivalence, these guys, the conjugacy to preserve time, and it's a very, very strong condition when it comes to flow. So not being allowed to modify the length of the orbits. And this equivalence for flows is essentially the counterpart to the equivalence I defined for diffeomorphisms. And this difficulty for the flows to remain with the same time is exactly what implies the rigidity we are seeing for diffeos, and actually similar results hold for flows. And that's what, essentially the corollary of what I said is that under the suitable conditions of whatever codimension and dimension, if two flows are time equivalent, so time preserving equivalent, then they are smoothly conjugate. Okay, I think I spoke more than I should. Thanks.
Wonderful, thank you very much. Are there any questions? Just remember to unmute yourself if you ask a question. Okay, so let's thank Federico again for this beautiful talk. And we will reconvene in 30 minutes. Federico, what happens if you strengthen your equivalence relation to look at several functions, not just one?
Well, actually, that's what we do. But even though it seems like faking and not giving you much information, we take the phi compose f, phi compose f squared,
I see,
and so on.
But they are all cohomologous, no?
They are all cohomologous, yes. But it helps in doing this game of thinking the phi as a coordinate axis. So this observable you think as the coordinate guy. Actually, this idea was already in a work by Takens in the 70s, where he proved this Whitney embedding theorem, but using observables. So, so it's the very same trick you apply here. Even though they are all cohomologous, then you really embed your manifold, and here is the same. So, of course, you can do it more seriously and straighten it to two serious potentials, and we do it for just in a complete general framework, you take the log of the stable potential and the log of the unstable, the log of the stable Jacobian and the log of the unstable Jacobian. And in this case, of course, it's very delicate because of the smoothness of this object. That it is only smooth, so one is only smooth along stable, the other is only smooth along unstables, and then between both you start to try to recover better smoothness. But well, that's all work in progress.
I see. That's very nice. And suppose you only know that these PCP sets are equal modulo Z or modulo some.
Good. Actually, modulo Z essentially would be okay. But here is, if you want a question about that. So take all, it's essentially equivalent to what I'm discussing. Take any flow, any Anosov flow, could be geodesic flow if you want. And look at the group generated by the length, the additive group generated by the lengths of periodic orbits.
Yes.
Now, if the rank of this group is 1, then you are suspension, because all are multiple of the same guy. You can, I think it is correct what I'm saying, that you can show that the rank cannot be 2. So if the rank is 2, it's actually 1. So it's really not 2. But my question is, can it be finite rank? So which would mean, so this translating your question, so assume this PCF mod Cn for some Cn is, they are matching. So can this cohomology be finite? And I don't know the answer. So I think it's very nice. At some point, the city of us, I thought it was an easy problem, but then when starting to write the proof, it was simply not working, and I have no clue of how to deal with it. So yeah, I think that for geodesic flows, I don't know. I honestly don't know enough. For geodesic flow on surfaces, whether this is finite rank or not finite rank or cannot be. So it's probably related with some arithmetic properties.
I think for contact flows, some things are known. Some
because they have. You're right.
Strong mixing and shadowing, so it should be infinite rank, dense, and everything I would expect.
Yeah.
That might be quotable from somewhere.
Yes, it's true.
Oh, wonderful.
This is amazing stuff. I never thought about the rank question, right? Just about rank 1 or dense, right?
Yes, exactly. Yeah. Yes. Yeah, and actually, so the idea for the proof for the higher rank, and that's why it wouldn't ever work. So I try just to do the same you do for rank 1. So in rank 1, you coach and you go to the circle, and the circle is as good as a Abelian group as any other guy, and you just push the theory there. And then I said, okay, you have Zn, then you go to the torus Tn, you just do it there, and no, it's not so good. So yeah, because you are a line inside the torus Tn actually. So your elements are in torus Tn, but it's a line in torus Tn, and it's a dense line in torus Tn. And so when you try to do something, you get nothing. But I'm sure there should be something. So something should be able to be recovered from this information of finite rank for these periods. It shouldn't be possible.
And maybe the Pinsker factor.
Yeah, well, it is some sort of joint Kronecker factor. So yes. So. Yes, thinking it more spectrally, even better. Yes, actually. maybe this helps to build examples. Yeah, because anosovs are very rigid objects, but pseudo-anosovs, on the other hand, are a little bit more flexible. And probably one can build this other rank for pseudo-anosov, because all this is attached to the amount of homology your manifold admit. So if you take the suspension of an Anosov diffeo, then the homology is 1 of the manifold. So you should have this circle, and that's it. Now, if you take a pseudo-Anosov diffeo, then the action on homology of the pseudo-Anosov could be identity. So there are plenty of these guys. And then when you take the suspension of this pseudo-Anosov, the homology of your manifold is larger. And then these periods typically go and inject into the homology of the manifold. And then maybe from there one can show examples of finite rank. So, because you have this sort of translation or rotation torus coming from your pseudo-Anosov, so this factor coming from there.
Interesting.
Yeah, no, nice. Yeah, that would be nice, because on the other hand, for this cohomological type of question, so being Anosov or pseudo-Anosov is not so much of a difference. So
Okay, so good evening, everybody. Good morning to some of you. Please could I remind you to mute yourselves. It's my pleasure to introduce our next and last speaker for today, Wenkai Liu from Texas A&M University, who's going to talk about small denominators and large numerators of quasi-periodic Schrödinger operators. Please go ahead.
Thank you for the introduction. First, I wanted to thank the organizers for the invitation. It is my great pleasure to give a talk in the conference. So in today's talk, I'm going to speak about the small denominators and the large numerators of the quasi-periodic Schrödinger operator. You may hear a lot of experts talk about small denominators before, so the new ingredient in this talk is the large numerators. So let's start with our model. So in this talk, I'm going to talk about the quasi-periodic Schrödinger operators, specifically for the one-dimensional case. So the operator is defined on L to Z. So the operator is given by here is the free Laplacian plus the potential. So the potential has a coupling constant here, lambda. Then we have a potential V. V is an analytic function on the torus. And the alpha is the frequency, and the theta is the phase. So for fixed potential V, we have 3 parameters, lambda, alpha, and theta. So if you write down this matrix in write down this operator in an infinitely dimensional matrix, the off-diagonal entries is given by 1 from here, and here is also 1 from this guy, and the rest is 0, and the diagonal entry is given by the potential V. So this is a tridiagonal matrix, infinite dimensional case. So we can ask a lot of questions about the quasi-periodic Schrödinger operator, for example, the spectrum. So the bigger problem is, one of the bigger problems is that people believe that for any analytic function V, this spectrum is a counter set. We know that Avena and Jetoviskaya, they prove that the 10-Martelli problem, which says that when the potential V is cosine, the spectrum is a counter set. And I can also study the spectral types of this operator, namely absolutely continuous spectrum, synchronous continuous spectrum, and the pure point spectrum. We can also study the dynamics. I will talk about it later. We can write down this system, this operator in your dynamic system. We can also study the spectral gaps. So many questions here. So in this talk, we are going to study the spectral types of this operator. So let me give you 2 extreme cases. So first, when lambda is 0. So when lambda is 0, which means there is no potential. Then this operator is just a free Laplacian. In this case, it's very easy to compute that the spectrum is exactly negative 2, 2, 2. And actually, the spectrum type is purely absolutely continuous spectrum. No synchronous continuous spectrum, no pure point spectrum. So another extreme case is lambda is infinity. When lambda is infinity, from here, you can think that after a scaling, which means there is no Laplacian, it's just a diagonal matrix. For diagonal matrix, which means the spectrum is a pure point spectrum, and the corresponding eigenfunction is just a delta function. So in this case, it's only pure point spectrum. So the general picture for one-dimensional case is that for small lambda, we expect this operator still have absolutely continuous spectrum, like lambda equals 0. So when lambda is large, we expect the spectrum type is purely absolute, is pure point spectrum. Like the case lambda equals infinity, we also expect for large lambda, the eigenfunction is localized. We call Anderson localization. So for intermediate lambda, we expect the operator has a singular continuous spectrum or has mixed types of spectrum. The general picture. So after decades of work, there are many experts made contributions to this area, but I just listed some of them here. So the first spectrum transition line of this operator was well understood. So I'm going to talk about what's the meaning of this, of the first spectrum transition line. So the first, before we stated the first spectrum transition line, I wanted to introduce several concepts. So first, we have the k-step transfer matrix, which is given by the multiplications of the products among k matrix. So the matrix AE theta is given by this 2x2 matrix, which is in SL2R. Then this is the first matrix. The second matrix, you shift this theta plus make it theta plus alpha, then make it theta plus 2 alpha until theta plus k minus 2 alpha, k minus 1 alpha. Then you get the k matrices. So why do we introduce the k-step transfer matrix? Because when you study the eigen equation, then you have that from the site M to site plus M, the relationship is given by the transfer matrix with changing the initial phase at theta plus M alpha, which means that from the site M to site MK plus M, the relationship is exactly given by the transfer matrix k-step, transfer from M to K plus M, with you change the initial phase theta to theta plus M alpha. So we can introduce the Lyapunov exponent, which is the average of the exponential growth rate. So first, this null is bigger than 1, bigger than 1, then we have the Lyapunov exponent is non-negative. So the first spectrum transition actually can be characterized by the Lyapunov exponent very well. So this is mostly by Avela's global theory. So let me introduce a natural dynamic system here. I start from theta, I change theta to theta plus alpha, then the vector in R2, I just multiply this matrix, I do the multiplication. You can see that this dynamic system actually is from the transfer matrix. So here is our dynamic system. So the dynamic system can characterize the spectrum types very well. So first, the energy E is not in the spectrum, is equivalent to that the dynamic system is uniformly hyperbolic. So these are all the results due to Jump and Moser. Then, and what we can say more. So for the first, then in the case, the Lyapunov exponent is 0 on the spectrum. So here we did more after complexification. So you have Lyapunov exponent E. Then now I do the complexification. We add an imaginary part in the Lyapunov, in the energy, make E to E minus E plus I epsilon. So if even after your complexification, the Lyapunov exponent is still 0. In this case, you can basically show the almost reducibility of the cocycle. So we call this cocycle. And then you can show it has purely absolutely continuous spectrum. It looks, very abstract. So I can give you a concrete example. For the one-dimensional shading operator, you can show that there exists lambda naught, which only depends on the potential V, such that when lambda is smaller than lambda naught, then the Lyapunov exponent is 0 after complexification. So which means that when lambda is smaller than lambda naught, you have this operator has purely AC spectrum for any alpha theta. So we know that when lambda equals 0, this operator only has purely AC spectrum. Now we show that when lambda is small, under small perturbation, the operator has purely AC spectrum. So this is corresponding to this case.
Could I interrupt for a minute? When you say complexification, do you mean that there exists an imaginary term epsilon for which something happens, or for all epsilon non-zero?
Oh, that's a good question. So there exists some small epsilon such that after complexification, this Lyapunov exponent is 0.
Okay, thank you.
Yeah, good. Yeah, small, because epsilon is big, super large, definitely the Lyapunov exponent becomes positive. So only there exists a small epsilon. Yes, a very good question. Yeah. So then you should know that it's kind of clear here. Then when lambda Lyapunov exponent is positive, so positive, this region corresponds to the
I'm sorry, Evans, but basically this point that sorry, I will start my video. Basically, the fact that the Lyapunov response is zero, your second point is simply a simple consequence of perturbation theory, because we're talking about very, very small lambda. Is that what you mean? Yeah. Okay. Thank you.
Yeah, small lambda, we have this Lyapunov point is 0 of the complexification.
No, I'm saying that this is basically a consequence of simply perturbation theory.
You mean it has absolutely continuous spectrum?
Yes, because the absolutely continuous spectrum is stable under small perturbations.
No, it's not that simple. Basically, the final proof is it's very complicated.
Okay. Thank you.
Yeah, pretty good. It's not that simple. Basically, the final proof actually it takes decades to finish the final proof. So finally, it's proved by Avila in 2009, something like that, around that time. Yeah, it's not just AC spectrum is stable. So we expect this proof in this region usually actually is easier. So this is why in this region actually the proof is more, the problem is more difficult.
Yes. Yes. Okay. Thank you.
So. Yeah, just like Mira mentioned, so for this region, it looks more reasonable, and for this region, when the upper opponent is positive, then it corresponds to non-uniformly hyperbolic. So in this region, it's not we expect purely point spectrum actually not clear. This is the region we are going to focus in this talk. So and for the intermediate lambda, which means that the upper opponent is 0 on the spectrum, but once you have an imaginary part, the Lyapunov opponent becomes positive. So no matter how small you are. So this is this region. This region usually it corresponds to the singular continuous spectrum. So in this talk, we are only going to focus on the almost massive operator. Actually the result can be more general. So we focus on this potential, which is only given by the one trigonometric function, so cosine. For this operator, the Lyapunov exponent can be calculated explicitly, which equals log lambda maximum of between log lambda and 0. So then which means when lambda is less than 1, you can show that this Lyapunov exponent is 0. Actually, it's 0 even after complexification. So you can show this is by Avila. Actually, the epsilon can be log lambda negative divided by 2 pi. So in Avila's paper, then it means that this operator has only purely continuous spectrum for every alpha and theta. So the final proof, as I mentioned, is given by Avila, but there are a lot of people made contributions to this region. So when lambda equals 1, then the Lyapunov opponent is 0. But after no matter a little complexification of epsilon, the Lyapunov opponent becomes positive in this case. So in this case, finally, it has been proved that this operator has purely singular continuous spectrum for any irrational number alpha and theta. It's also clear. So now we are care about this region lambda is bigger than 1. When lambda is bigger than 1, so the Lyapunov opponent is positive. We call positive Lyapunov opponent region, so supercritical region. So in this region, by Courtney theory, also last assignment, first we have that this operator does not have any AC spectrum. So Lyapunov opponent is positive, so no AC spectrum. So we are interested into this spectrum transition line, which is called a second transition line. So let me give you a graph. So now when lambda is 0, we know AC spectrum. So lambda is infinity pure point spectrum. So lambda equals 1. Sorry. Lambda equals 1 is singular continuous spectrum. This region is pure, AC spectrum. We expect there is a second transition line here, such that in this region is still singular continuous spectrum. In this region is pure point spectrum. Because
my apologies, but for as far as I know, maybe there are new results which I'm not aware of, but as far as I know, for the critical case lambda is equal to 1, there is a discrete set of thetas for which we still don't know whether it's purely singular or continuous.
Yes, but it has just been proved by Nana last year.
Ah, okay.
This paper just got published probably 1 month ago. Yes.
Thank you.
Yeah, very good. Yeah, finally, many results. Good question. So it finally, got approved. So now, in this region, as mentioned by Cottani theorem, there is no AC spectrum, so only singular and a pure point spectrum. So we expect there is second transition line here. So before I state the second transition line, let me give you some prediction. So let us guess where should the second transition locate. So for the first transition line, you can say it's characterized by the Lyapunov exponent. But now let's talk about the second transition line to say, to kind of guess the second transition line first. So then I needed to introduce the phase and the frequency resonances. So the phase and the frequency resonances, we wanted to start from the lambda equals infinity to do the perturbation, to say how far away we can go from lambda equals infinity to predict the second transition line. So we start from lambda is infinity. For lambda is infinity, this operator is kind of diagonal matrix. So the eigenfunction is corresponding eigenfunction is delta function, well localized. So you wanted to do the perturbation, you need to study the separation of these eigenvalues. So unfortunately, when lambda for the diagonal matrix, the eigenvalues is given by the cosine, right? Is the diagonal entry. So this set, the eigenvalues are dense in the range. If they are dense, it's very difficult to do the perturbation. So, and we can study the difference, as I mentioned. If we wanted to do the perturbation, the separation between two eigenvalues are important. So the separation, the difference by some simple calculation, trigonometric identities you get equals lambda 2 theta plus k1 plus k2 alpha, k1 minus k2 alpha. This is distance, and this is the nor is the distance to the nearest integer. So now I'm ready to introduce the strength of phase and the frequency resonances. So the frequency resonances, which is given by the limited soup of this quantity. So you can say that this is less than or equal to 1, which means that this beta alpha is bigger than 0. This guy is also bigger than 0. This is called phase resonance. So why do we introduce these two guys? So let me give you some hints. So forget about let me cheat you a little bit. Instead of limited soup, which I think here is limit. If here is limit, let's go to this guy. The separation of two eigenvalues actually is E log lambda, because lambda equals this function. And this guy, the second quantity is given by E k1 plus k2 delta, more or less. The third guy is E beta k1 minus k2. So what does this mean? This guy, as I mentioned, is the Lyapunov exponent, which means that when Lyapunov exponent is bigger, lambda is larger, the separation is better, then which means it helps us to do the perturbation from lambda equals infinity. It helps us to have localization, to have a pure point spectrum. On the other hand, if delta is bigger, beta is bigger, which means the separation is bad, which is worse. It prevents us to do the perturbation. It prevents us having pure point spectrum. So there is a natural competition between the Lyapunov exponent and the resonances. So it's believed that the spectrum type of H, either singular continuous spectrum or pure point spectrum, depends on the competition between the Lyapunov exponent and the resonances are associated with 1 and 2. These two guys. So kind of natural. So such observations goes back to Avery Simon, Gordon, and Jitomi Simon. So after all the preparations, I'm ready to state the second spectrum transition line conjecture, which predicts where is the second transition line located. So basically, in early 1990s, Jeton basically conjectured that the transition line happens at the point the Lyapunov equivalent equals both resonances. So you compete. So now I'm give you the graph again, picture again, lambda 0, lambda infinity. Here, lambda equals 1. As mentioned, the AC spectrum, singular continuous spectrum. Here is pure point spectrum. The second transition line is lambda equals E delta plus beta. So more precisely, when lambda is less than Lyapunov, which means resonance beats the Lyapunov equivalent, then singular continuous spectrum in this region. However, when Lyapunov equivalent beats the resonance, we have the Anderson localization. So Anderson localization, which means that only pure point spectrum plus exponential decaying eigenfunctions. As I mentioned, that when lambda equals infinity, pure point spectrum, the eigenfunction is delta function well localized. So we expect that in this whole region still have the similar property, pure point spectrum plus exponential decaying eigenfunctions, we call local Anderson localization. So this is the second transition line, which is this point. So now I want to talk about some positive results, positive answers to this second line spectrum transition conjecture. So I forgot to mention one result. So in Jeton-Miskaya's similar result, when delta alpha equals 0, beta alpha equals 0, when both of the resonance are 0, she proves that when Lyapunov equivalent is big, when lambda is bigger than 1, then we have Anderson localization. You say when beta and alpha both equal 0, which means that this transition line collapsed, overlapped with lambda equals 1. So the whole region has Anderson localization, which is by Jeton-Miskaya, 1999 paper. So we have another two results in the last several years. So first, when delta is 0, so which means that there is no phase resonance, then we can prove that this conjecture. There's two cases. So another part is proved by Avila, Yu, and Zhou. So when beta equals 0, then we also prove this conjecture several years ago, which means that, but in these two cases, basically there are only single resonances, right? Because one resonance is 0. So this is the low-end results. So what we are going to talk today, so we wanted to introduce a family of phases, which is called a completely resonant phase. So we say theta is completely resonant with respect to frequency alpha is 2 theta in this family set, which is just Mira mentioned. So this special kind of family set, actually, people didn't prove the singular continuous spectrum for lambda equals 1 before, because this family of phase is special. So another importance of the family of phase we call completely resonant phase is that by upward duality, this completely resonant phase corresponding to energy with the rotation number in this counterbody many set. I don't want to mention upward duality, but this theta is important. It's equivalent to the rotation number in this counterbody many set. And finally, this energy is corresponds to the spectrum edge. So that's why this family of phase is quite important. So as for this phase, for example, for simplicity in this talk, you just think theta is 0, because theta 0 is in this set. So for this set, if we go back to the second spectrum transition line, if we go to the definition, theta is 0, so which means that beta alpha and delta are equal. So we have both resonances appear and the strengths are the same. Then by the second spectrum transition line conjecture, which means that we expect when now the Lyapunov equivalent is bigger than 2 beta, we have the localization. So since this particular family of phase is important, so in Avila and Chetomisky's 10 material problem paper, they restated this conjecture. Mentioned just for this phase. For this phase, and the localization, if the alpha opponent is bigger than 2 beta. As I mentioned, this conjecture is a particular case of the second transition conjecture. So what's the main result of the talk? So basically we prove this conjecture as it is. So what's the new idea in this proof? So we initiate an approach to simultaneously treat numerators and the denominators of Green's function of quasi-periodic shading operator. So in the following, I'm going to tell you what's the Green's function, what's the numerators and the denominators, and the new ideas in our proof. So before moving to the proofs, so any questions?
So basically, your proof is particular for the almost matter operator.
Yes, for the particular phase.
Is something in that spirit I'm not sure, but is something of that spirit can hold for general quasi-periodic operator?
You mean no, only for the almost massive operator.
So yeah. This is particularly suited for just this conjecture for the almost matter operator.
Almost matter operator, yeah.
Thank you.
But people believe that probably it's true for even function. Because cosine function is an even function, so there is some people think.
Will something like that be true for functions of the type from Sinai's paper in the Morse functions, but just with a finite number of maxima and minima?
So that part I didn't know. Yeah, I don't know if it's it's true for the the potential studied by Sinai one maximum one minimum like the cosine type of function. Yeah, I'm not sure. Yeah.
You're not sure.
So now I'm going to talk about the proof. So the first step is going to reduce this problem to the study of the Green's function. So by Schnorr's theorem, in order to prove the localization, we only to prove that for any question.
What is Schnorr's theorem? Are you going to say?
Oh yeah, that is the theorem. This is the following theorem. Yeah, good. So Schnorr's theorem says that basically that the spectral measure supported on a generalized eigenfunction. Here, generalized, which means that any eigenfunction solve this eigenequation, but this eigenfunction is polynomial bounded. So for almost energy E, almost every energy here, almost every means that with respect to the spectral measure. So which means that in order to prove the localization, we only need to prove that for any generalized eigenfunction, as I mentioned, is a polynomial bounded eigenfunction, you can finally prove it's localized eigenfunction. That's it. So you only need to prove this case. So this is very important, the first reduction. So now we are able to introduce the Green's function. The Green's function is simple, is the inverse of the cutoff matrix. So you choose an interval x1 and x2. You cut off this matrix on both sides, you get the inverse. So definitely this Green's function depends on lambda, alpha, and theta and the energy E. So we drop the dependence in this talk. This Green's function. So now let me introduce the strategy to prove it. The first strategy was originally from Chetomisky's 1999 paper. So we have suppose now this is the generalized eigenfunction. You just solve it, you get this formula, and this is because this original matrix is a tridiagonal matrix. So you have y here, you have an interval x1, x2, then you get x1 minus 1, x2 plus 1. So you get this nice formula. So in order to prove the localization, we have this is the two steps. The first step, you show that the Green's function, this guy and this guy, are exponentially decaying. Since by Snow theory, this guy is polynomial bounded. This guy is polynomial bounded. I wanted to show phi y is exponential decaying. I only to show that these two guys are exponentially decaying. So, but this is not enough, because if here is 0, here is y, you show this Green's function is exponential decay, but maybe this size is too small. Then you need to continue to do several block, we call block expansions. So first step, you show this Green function is decaying like this, which my decay rate is this guy. And then you get this point. You replace the y with x1 minus 1. You continue to do the expansion from this point, then to this point, then until you reach 0. We call block expansions. So finally, you can prove it's able to allow you to prove decaying with the size y. Because maybe the interval you choose along the y is too small, you need to do many steps to get the enough decaying rate. So the block expansion is quite standard. The difficulty is to get the exponential decaying of the Green's function. So Bogan has a book in 2005 which just studied the Green's function. So basically, this is the main ideas. So now I'm going to talk about this, how to establish the exponential decaying of the Green's function. So let me denote the determinant of the matrix, the cutoff matrix, by P. So by Cramer's rule, it's very easy to calculate the two guys here, Green's function. Here, sorry, let me clear the page. So these two guys can be calculated explicitly by the determinant. So here is also the formula is all due to that the matrix is a tridiagonal matrix. You have x1, x2. Here now you have y. So you get a y plus 1, y minus 1. So you get the determinant of this matrix, determinant of this matrix, and the determinant of the whole matrix. So then we have the denominator. They have the same denominators, but the numerators are quite a little bit different. So in order to show that the Green's function decays, we only need to show that this denominator cannot be small. Then we have the small denominator problems. At the same time, we wanted to show that the numerators cannot be big. So traditionally, people only study the small denominators problem because the numerators can be bounded easily. So the numerators can be bounded just by by the Lyapunov exponent, which is from the upper semi-continuity and the unique codicity. You can study this guy is bounded by the Lyapunov exponent. So numerators is easy to deal with. Then the difficulty is the denominator. So the good thing is that averagely speaking, the denominator is also has a lower bound than the Lyapunov exponent. We can averagely speaking, the denominator is big. Because actually, by the definition of the Lyapunov exponent, the lower bound actually must average is controlled by the Lyapunov exponent. So averagely speaking is good, but this is which means in average, the denominator is very big. So if you can prove this is not average, is for individual theta, for every theta, then the problem is done, because you show that individual theta there is no small denominator. The denominator is big, and the Lyapunov exponent. Then you can finish everything. As I mentioned, you can prove the Green function is exponential decaying. You use the block expansion. You finish everything. But the difficulty is that this is not average. It's not individual theta. Then its average is very big. Then this is the difficulty. Then we need to use the small, the large deviation theory and also study the trajectory to deal with the small denominator. So large deviation theory, which means that for most of theta, this is true, right? Because average we know it's true. And we also need to study the trajectory. So where is the trajectory from? So let me explain to you a little bit. So suppose you have y. We want to find an interval x1, x2 such that this p x1, x2 here has a big denominator, is big. So what's the idea here? We shift this interval by 1 unit. If you shift this interval by 1 unit, then since that potential is theta plus n alpha, which means that you shift this interval by 1 unit, it means that we have this quantity, which means that you shift theta by 1 unit. So this is the very, very good thing. So it means that if you allow you shift L in your long scale, by the ergodicity, definitely you can achieve this average. So however, you can only shift L in this small size because you need to guarantee Y is in X1 and X2. Which means you can only shift L in a small region. So the problem becomes, can you find the proper X1 and X2 such that you shift L in this small scale here? Can you guarantee there is no small denominator? So this is the problem. So now I can give you one example how to deal with this case. So we can give you just wanted to build some connections between this, how to deal with this denominator with the resonance, because finally we wanted to prove that resonance and the Lyapunov polent control everything. So one example, we can use the Lagrange interpolation theorem, because this matrix, let K be the size. This matrix, since the diagonal entry is by cosine, so finally this matrix, the determinant is a polynomial of cosine function. We wanted to use the Lagrange interpolation theorem. We just choose this point. You can say the difference between 2 points is the exact difference for the unperturbed eigenvalues. So basically, there is some connections if we use Lagrange, connections. So I mean, I just wanted to give you some, intuition. There is some connections between the small denominators and the resonance. So now I'm able to talk about the strategy in James Tokay's 1999 paper. As I mentioned, this average is big. Then she showed that when beta is 0, delta is 0, there is no, the resonance are basically 0. Then she showed that for L in such kind of scale, this denominator has one L which is big. Then this is one critical part for her to deal with this undersynchronization, but the actual proof is more complicated because in this case, L is in a consecutive interval, but in her proof, she needed to choose 2 intervals. So L in this interval or L in another interval, but this is just a simple, case. I wanted to give you, explain to you. So this is her idea. So as I mentioned, finally we proved this case when there are only single resonances, either delta equals 0 or beta equals 0. So let me remind you that in the term-multiple problem, they prove that when delta equals 0 and the Lyapunov polent is bigger than 16/9 beta, then they prove undersynchronization. So, and my collaborator pushed the limit to 3/2. And finally, as I mentioned, we prove that when there is only single resonance, if Lyapunov polent beta is bigger than beta, or Lyapunov polent is bigger than delta, then we have the localization. But what's the new idea in these 3 papers? So there are many ingredients there, but I wanted to mention one ingredient, so which is that the Green's function is not necessarily exponentially decaying. So what is the idea here? Let me remind you that we have phi y equals this formula. As I mentioned, I continue to expansion. So the idea is that even though this Green function is not exponentially decay, even though it grows fast, but if the second Green's function do the expansion, it decays super fast, we are still safe. We compensated the first one. So this is the idea inside. So we studied this Green's function very well to say some Green function, you are close. Some Green functions decays, but it's fine. We compensate with each other. So then we get this final proof. And another ingredient in this proof that we highly use the continued fluxing expansion to deal with the resonance. So let Pn over Qn with the continued fluctuation approximation to alpha. So now I'm ready to talk about the new ideas in my proof. So first, we deal with the non-resonant sites. So let me only focus on the scale 0 to Qn. So let me give a picture. Here is 0, here is Qn. So non-resonant sites, which means that this guy y is not, here is half Qn. So non-resonant sites, which means that I choose the y in this middle. But you choose y in this middle, we have 2 theta plus K1 plus K2 alpha. This is 2 resonance. And we also have K1 minus K2 alpha resonance. So, and now K1, K2 is in these 2 regions. In this case, as I mentioned, you can think theta is 0. For simplicity, we just think theta is 0. So now theta is 0. In these 2 regions, you can say K1 plus K2 is not in QNZ. K1 minus K2 is not in QNZ. Right? Because this is half Qn. I'm far away from half Qn. When K1, K2 in both these 2 regions, this is not in QNZ. This is not in QNZ. If this is not in QNZ, there is no small denominators. Kind of, there is no resonance. So in this case, actually the proof is very similar to James Cass' 1999 paper, because you have the resonance, but it's not. It's far away from the resonant sites. It looks like non-resonant sites by the basic continued fluctuation expansion. So this is the first case. So now the difficulty is to deal with the resonant sites. So now I also focus on 0 to Qn. Resonant size, as I mentioned, is either half or Qn. So in this case, I just choose this half Qn. Then in this region, first, the idea is that we need to choose all the approaches I mentioned before to deal with the localizations, plus the following new ideas. So now the first idea is that we need to treat the numerators. Before, we simply bound the numerators by the Lyapunov polent from the unique ergodicity. But here we can do more. So now let me give you some hint. This basically is from the Floquet theory. So now imagine alpha is periodic. When alpha is periodic by standard Floquet theorem, on the spectrum, the numerator actually grows at most linearly. Actually, we can say more. When the energy is in the spectrum, inside the spectrum band for the periodic shading operator, the P, actually the numerator is bounded by Floquet theorem. But when the energy hits the spectrum edge, it grows at most linearly by the standard Floquet theorem. So which means that we can do something here. So now by the continued fluctuation expansion, this 2 guy is more or less, by our definition, is E beta alpha Qn. So when beta is big, which means that we have a strong resonance, it prevents us to have localization. But on the other hand, this is a good thing we can play, because beta is big, which means that alpha can be approximated by a rational number very well. If it can be approximated by a rational number very well, for rational number, it's a periodic operator. The numerator is super small. So which means it's a good thing we can use. That's why we use the periodic shading operator to do approximation to estimate the numerator. So actually this idea has already been used starting from Gordon. We use this idea to prove the singular continuous spectrum before, but now we borrow it to prove to establish the upper bound of the numerator. So this is the first idea. But if we just use this idea, it's not enough. So we needed to do more. So let me give you the second idea in the proof. Second new idea. So now imagine you have x1, x2, you have y. So now you have y plus 1, 1 minus 1. We know that the numerator, this is the denominator of y. This is the numerator of y. So imagine this guy is big. From y plus 1 to x2, imagine this guy is big. This guy is big, which means the numerator is big, which means that it is very bad for y. But it's bad for y, but we can do something here. Because if it's bad to y, I choose y prime inside. Well, consider about this interval. This is my new x prime, y. x2 prime. This guy, y1 plus from y1 plus 1 to x2 is the numerator for y, which is bad if it is big. But it is the denominator of y prime inside, which means if it's big, it's very good for y prime because it's denominator of y prime. Then that is something we can do, we can play. So finally, our idea is that we use the numerators as the variables and established a lot of relationships, inequalities among the numerators, among the eigenfunctions. We solve those family, a lot of inequalities to achieve our final proof. So this is the idea in our proof. There's some new ideas in our proof. Unfortunately, I didn't have time to explain all the details, but I hope you can understand the new sense behind it. So that's all I wanted to say today. Thank you.
Thank you very much. It was extremely interesting. Are there any questions or comments?
Yes, I have a question. I'm sorry, I'm trying to understand what exactly from the almost Matthew you using heavily so that you cannot extend this for let's say at least trigonometric potentials. So I presume you using Chambers formula.
Kind of. Yeah. So if you use it, yeah, good idea, good question. So because when we use if there's a polynomial here, we wanted to finally to start, this guy is a polynomial of the cosine. If you have several trigonometric functions, then the degree of the polynomial is too big. So we cannot show that it decays for everywhere, but we can show that your scale of 0. So what can I say? So for almost as operator, we can show the eigenfunction decays everywhere. But if you give me a trigonometric function like the degree is d, finally we can only show the density of the decaying of the eigenfunction is basically 1 over d, because you cannot prove everywhere the eigenfunction is decaying. We can only show the density is 1 over d because this is the polynomial.
Oh, yeah. So you're actually using the structure of the eigenfunction itself. So you're using the knowledge about the eigenfunction.
Yes.
Of the almost Matthew. So it's not only just the Chambers formula, but you're actually using your previous knowledge about the structure and about what you know about concrete eigenfunction for the almost Matthew. Do I understand correctly?
It's not like that. I believe it's because this polynomial, we study the determinant, we need to consider about the degree of the polynomial.
So you think that this result will not be true for the trigonometric polynomial?
Yeah, we cannot prove for the trigonometric function, but we can show that, as I mentioned, the decaying for the eigenfunction, we can prove that the density of the decaying is like 1 over d if they give me the degree is d over trigonometric function. So this is something we cannot do. Yeah. Unfortunately, yeah.
Okay, any other questions or comments? So let's thank the speaker. In fact, all of today's speakers again. And we reconvene again tomorrow at 2 p.m. Moscow time. Good evening, everybody.
Thank you very much.
Thank you very much.